organization architecture, and
Mhm.
see, COA will help you to understand how these mappings are done, how the okay, I mean, I can't explain it without saying those terms, but so basically that is, but uh, overall management, right? Overall
Mhm.
management is done by operating system. So COA actually is, I mean, nearer to the hardware part of it. Operating
Okay.
system is the manager. It's like the manager of a company, and COA is and the or COA is basically dealing with the employees who are making the things. It's something like that.
Okay.
Yeah, so maybe if we have we are planning to have some degree level courses in these kind of topics. So if we have that, then that would be, these answers could be cleared over there. I mean, I hope.
Yes, sir, sure.
Fine. But you can always post on Discourse if you want to discuss these things. If you have some doubts, if you want to
Mhm.
just have a open discussion, please post on Discourse and we will try to answer or discuss. Fine.
Okay, sir, sure.
Okay. So 11 people joined at 6:11. So let's start. See, so what we are planning to do today is I would try to go through all the codes of all the algorithms of week 5 and week 6. Fine. Week 6 is mostly about the tools and then implementing them in week 5 algorithms. And in between, obviously, we have to revise some theory parts. Otherwise, we cannot, as the part which is required for that algorithm to work, we will discuss only those parts. And then we will try to have a line by line execution of the programs that were there. Fine. So this is so in this session, I would request you to ask your doubt whenever it is happening. So we would try to run the code line by line and then see what happens. So whenever you are facing some doubt, whenever you have any question regarding a specific execution, please ask at that time. Fine. Oh, okay. So is my screen visible?
Yes, sir.
So I mean, you can see the code editor, right?
Yes, yes. Good.
Okay. So let me just yeah. So yesterday, yeah, you want to say something? Okay. So yesterday we were actually closing the discussion by having a little bit of questions and discussions on the Dijkstra algorithm. And so let's start Dijkstra algorithm, the basic Dijkstra algorithm. Let's start that and see how it works. Fine. So I would assume that at least the theoretical part of it, you all know. Fine. Any questions in the theoretical part? Because unless and until that is clear, that picture of proceeding step by step, what you do, unless and until that is clear, you cannot understand the code. Fine.
So can you repeat that in just like a short summary?
Okay, so that would be a very short summary. And yeah, in that case, that would be a very short summary. Huh? So if we have multiple vertices, if we have like this, multiple vertices are there, right, in a graph, and right, and this is my start vertex from where I have to start my Dijkstra algorithm. So what do we want to do? We want to find the minimum path, that is path length to each of the vertices from the start vertex. So what is the process that we would do? The algorithm that we follow is, at first, obviously, since there is only, okay, let's add another like this. Okay, maybe add it in the other way. Yeah, fine. So this is my graph. Now S is the start vertex. The process that we would follow is step 1, that is all the edges that comes out of the starting vertex, right? You take that value, and if you see and put those values in the nodes, that is you put, so in the nodes inside the nodes we would put those values which represents the distance from the start vertex to that particular node. Okay, so that is the understanding. And in terms of programming, what we would do, we can take a dictionary, a distance dictionary. To each of the node, the distance of I is equal to the total path length from the starting vertex to the ith node. That is equal to distance of I. So that can be a simple dictionary. So now what we will do, since the start vertex S is there, so I would put 10 over here because that is the current distance through which we can reach this node. So let's call this is A, B, C. Okay, so 10 is there. Now, is there any other outgoing edges from my start vertex? No, right? There are no other outgoing edges. So that is the only edge that I have. In the meantime, I will have to store infinity value in all of these, because as this is minimum, I mean, we have to find the minimum path, right? So you initialize all the current value of the nodes with infinity. Huh? In fact, this 10 was also infinity in the start. Fine. And actually, let me just reiterate that. I missed that. Fine. So actually what will happen is you will do an initialization of infinity in all the vertices, and in the start vertex you would initialize with 0. Fine. And then what you would do, on the graph, every iteration you would find the minimum distance vertex in every iteration. Now what is the minimum distance vertex? I'm just repeating the algorithm in terms of the program, not the theoretical part, but the program. So that would be better. So you initialize the start vertex with 0 value. So distance of start would be 0, and distance of all other nodes would be the distance dictionary that I was talking about. So distance of the start vertex would be 0, and distance of all the other dictionaries which are, all the other vertices, right? A, B, C, D, whatever, that would be infinity. Okay. Now what is the next step? Next step is you would extract the minimum distance vertex. That is, you have to find the minimum distance vertex. So obviously the first start vertex, since it is 0, so that would be taken out because it is the minimum distance 0. Others are infinity, right? So 0 would be taken out. So what is the next step then? Once the minimum distance vertex is taken out, next step is you have to take all the edges and relax that. Relax means you have to take all the edges and allocate the distance value of all the neighbors. So who is the neighbors of the start vertex? A is the only neighbor. Correct. So what is the next work that I have to do? I have to compare whether the current distance to reach A, current distance is what? Infinity, correct? Current distance. It is infinity. I have done the allocation over here. Not allocation, initialization. So that would be infinity. So if my current distance to reach a vertex, and that vertex being the neighbor, so check all neighbors. Check all neighbors of V. Assume that this is the minimum distance vertex that we got. Fine. Check all neighbors of V, and then you do if the distance of the neighbor, right? Let's say the neighbor is any I. The distance of this neighbor is greater than the distance of what is the distance if to reach A if I have to go through S? It is the distance to reach S, which is 0 apparently, and the edge weight that connects S to A. Correct. So the distance of neighbor, if that is greater than the distance of V, which is the parent vertex, plus the edge connecting, right? Plus the edge connecting V comma name. I mean the neighbor. Right. And this from where we will get? We will get it from the adjacency list. Or if you take matrix, then that adjacency matrix, right? whatever. The edge weight we will get. So if this is the condition, if it is greater, then we would simply replace the distance with distance of the neighbor with this value. Fine. So every time we will check this, and obviously once we are over here, we modified the distance and we will set the visited part, right? We have visited this. So whenever we extract it, we set the visited that we have visited this one. Okay. So since we have extracted min over here, and then we are actually checking the neighbor of V, right? The V is the minimum vertex, right? And then we have proceeded to step 2. So before proceeding to step 2, we have to also set the visited of V to be true. That is, we have actually visited V and we have also visited the neighbors of V, right? So here, along with this condition, you again have to check one more thing, that if distance is greater than distance of V plus the edge and the visitedness, right? And if visited of my neighbor is false. If that is the case, then you simply change the distance. So every time we will check if this is the condition, then we would just decrease the distance and we would proceed likewise. That's it. And how many times we would do, unless and until we traverse all the vertices. That is, basically we relax. I mean, you can say it in either way. We traverse all the vertices, or you can also say we have checked all the edges. That also is fine. Either way. How to translate it in terms of code? You can simply traverse the vertices. That should work. Okay. As of now, once we go to heap, we will discuss something else. But as of now, just understand that. So if I do these steps continuously on the graph very quickly, what we will get? So I check 10, right? 10 is the path. So this V neighbor 10, this would be 10, and distance of V in case of it is, that means distance of 0, distance of the start node, which is 0 equal to. So 0 plus 10, I would get 10, and the initial distance of the neighbor was infinity. So obviously that is less. So I set this infinity to be 10. Right? Just apply the same. Now same thing would happen. Again, my iteration in the loop would come over here and it would try to sorry, it would try to find the minimum vertex. Right? Now if you check the minimum vertices, what have we got? We have 0, which is already done. So I am crossing this. We cannot come over here because it has already been visited. I have set this visited of that to be true. So next is A, which is not yet visited. And now infinity, infinity, 10. These three values are there. What is the minimum value among these three? 10 is the minimum value. So this result, minimum distance vertex, we would now actually pick your A vertex. Fine. Now once it picks up A, then you would again do the same steps, that you would take all the edges coming out from A, and I mean basically check all the neighbors of A and check this condition. This condition. So you check that condition again. So here you have 20, right? This edge weight is 20, this one, and your current value of the distance, right? This one, distance of V, because now V is A, right? So distance of V is, that means distance of A, which is 10. So I would get 10 plus 20, which is 30. Initially it was again infinity, right? For B. So I would simply add 30. Again, there I have one more vertex from A, sorry, edge from A, right? So we would also check that, and accordingly we would get 18 over here. Fine. And okay, so now this is also done. 2 vertices are out of the list. So 30 and 18 are the next two options. So 18 is the smaller value. So minimum distance vertex we will pick again. Pick 18 because 30 is greater than 18. And then what you do, you again same steps, you actually check for all the neighbors of 18 and I mean decrease their distance if possible. So see, I can see that only one neighbor of 18 is there. I mean C node, the neighbor of C node is only one neighbor, which is the start vertex. This is not a neighbor. I mean this is a neighbor from B's view, but not from C's view, because C cannot go to B. There is no directed edge towards B. So only one neighbor is there, which is my start vertex, but the start vertex I cannot visit. Why? Because it has already been visited. You see this condition, now it applies properly. If I would have not written this condition, then we would have again went back over here. And that is not correct, because anytime, since this is the start vertex, this is anyway would be 0. And we are going 10 plus 8 plus now whatever the length of this path is, let's say this path is 5. So 10 plus 8 plus 15, we have to check that. So it's not required to check all those. It's already visited. So we simply ignore that. So 18 cannot do anything else because its only neighbor is already visited. So we skip that. Next only value is 30, right? So 30 would be chosen as the minimum, only leftover one, and we would again check all the neighbors for 30. I mean the B vertex. So we see that 18 was already visited, right? And that is the only vertex over here. I mean, but only edge from B to C, right? There are no other outgoing edges from B. So, but 18 was already, C was already visited just before coming to B. So that is also out of question. So there are no other nodes left, only this one is left, and it has no other edges to check. So that's also done. So these are my values. So A would be 10, B would be 30, and C would be 18. So that's your Dijkstra algorithm. And I also discussed the code alongside. And now let's check. Okay, just have an overview, then we would quickly go through line by line execution. See, so these are the starting, like this is basically the algorithm, this much, right? So let's see what's happening. At first we are taking an infinity, right? So you can take it anyway, whatever infinity you want to, in whichever way you want to initialize it, you initialize. It should be a value which is greater than all the distances. That's it. And what are we doing next? We are taking the adjacency list, okay, and again initializing the visited and the distance dictionary. Visited dictionary is required for that visited check, right? Whether a node is visited or not, and distance is basically the current value current path length from the start to vertex B, right? So once that is done, see, I told you one initial start vertex, you would initialize the distance to be 0 and all others to be infinity, right? So this is the, see, all the other vertex. So we are iterating through the the adjacency list and setting the distance of all the vertex to be infinity, except this one we are actually modifying it to be 0, the start vertex. So obviously when my,
So
yeah,
we are doing this as a second step. First we initialize
yeah,
this also as infinity.
yeah, we do that. I mean, if you want, you can skip that. I mean, you can just in whatever way, anything. The main idea is before you come into the main part of the algorithm, it should be 0, because see, what I want is this minimum should pick the first vertex. That's the motive. Fine, that this minimum at line number is not there, but anyway, this minimum, it should pick the start vertex. That's the only idea that I want to have. And that's why we are making it 0 and all others are infinity. So obviously that would pick. Okay, you can set it to be any value, doesn't matter. The only thing does not, no, we cannot say doesn't matter. If you are later when you are adding the distance, then if you are adding any other value -1, then it would decrease. So anyways, so you have to make it 0, and the reason for that is we want it to be the first minimum vertex to be selected. Fine. Okay. So after that, what are we doing? We are actually running through all the vertices. wlist.keys, this basically is running through all the vertices, right? Running, that's it. Like in our algorithm, what we did, we actually checked all the vertices, right? This one, then we went for this one, then we went for this one, then finally we also checked this one. Although this last vertex did not have any other work to do because all other vertices are visited, but still we took it and then we popped it up. I mean, checked, is there any other edge to work? But there are no other edges. I mean, edge was there, this edge was there, but the vertex that it leads to has already been visited. So there was no other work. So we simply, we visited that and we ended the algorithm. So you basically visit through all the vertices. That's the idea. That's what this line is doing. Fine. And then we are just picking the minimum distance. which is not visited. So for the first iteration, it would pick obviously the first vertex. Now this line, what does this line mean? This is in a situation that is not there in our dry example that we just dry run. I mean, in our example that we just did the dry running on. But this is basically in a situation where you have more than one vertex with the same distance, and that distance is the minimum value, right? So in that kind of situation where both there are three vertices with the current distance as 10, and 10 is actually the minimum value of distance in all, I mean, at that current stage, minimum value of distance among all the vertices. So you remember that initially both of these two were infinity, right? Just a second. So yeah, both of these two were infinity. This was only 10, right? And that's why out of these three, this one, this infinity one, and this one, see, we actually pick 10. We are calculating the minimum value. But let's say in some one graph is there which is like this. So this is the start vertex. I have a node over here which is 5 apart, 5 distance apart, and again here also I have 5 distance apart another node. Okay, and there it is 8 distance apart some other node. Fine, then there is something else, right? In this situation, both of these nodes initially are 5 distance apart. Fine. So you can pick either one. Doesn't matter. Dijkstra would give you correct result in either case. Fine. But one algorithm should actually take one of them, correct? First, if obviously it takes this one first, and then it should take this one, because second minimum again would be this. If I take this node first, then after finishing this node, I would obviously have to take this one, because that was the second minimum, correct? Or the other way. So what we do over here is we simply create a list of all such minimum value, minimum distance nodes, right? Now, if there is in our current previous example, there were no such node which had, I mean, multiple nodes were not there with same distance. So the list would only store that one vertex. That's it. Okay. And see, this is actually the line which tells you can exit from, I mean, from the loop. You can exit this. The reason is if there are no other vertices, right? Same thing. We did it until we exhausted all the vertices, right? There were no other vertices left. There are no neighbors left actually. So if the list is empty, that means there are no other vertices left, right? So in that case, we can say that, okay, you can break the algorithm. You can return from the algorithm. Fine. So that is that condition. After that, what we are doing is we are just picking from the list that have the minimum value minimum value nodes. From that list, we are just picking any one. Now, any one here, we are doing that by using the minimum. That is, this minimum has nothing to do with the algorithm. Keep this thing in mind. The current highlighted part of the program, we are picking any one of the node from the group of node which had minimum distance at the current instant of time. Now, according to Dijkstra algorithm, you can pick any one of the minimum distance node. Doesn't matter. At the end of the day, you would end up with the correct answer. So the order of picking the minimum value node doesn't matter. Okay. But here we are doing it. I mean, in a program, you have to follow any one specific order for the sake of checking the output, right? So we are taking the minimum among that. That means this minimum is not with respect to distance. This minimum is only with respect to the vertex number. So let's say 0 means one vertex, 1 means one vertex, right? Since ultimately it's a list. It's a list that we created. So 0 is, so see, what does this tuple means? It means there is an edge from 0 vertex to 1 vertex whose length is 10. Correct. So 0, 1, 2, 3, 4, this is there. So we are taking the minimum of this means that means we are taking the earliest vertex, whichever 0, 1, let's say 0 vertex, let's say 1 vertex, 4 vertex, and 6 vertex. These 3 vertex has same distance. So this would fetch us the 1 vertex. That's it. You can also take the 6th vertex. Doesn't matter. Your code would give correct result. Okay. Finally, once you get that minimum value, minimum distance vertex, you check through all its neighbor. Set the visited to be true that we just discussed now. Set the visited to be true, and then you just traverse through all the neighbors of that. See, W list of next V. Next V is basically that node which is the minimum. So you traverse through all the neighbors of that, and then you simply apply that condition that I talked about. This one, this condition. Fine. And what is that? That whether the current distance of the vertex that is lesser this distance V is lesser, or the distance to reach V using the parent vertex, which is next V, plus the edge. I mean, that is basically the distance to reach V. So the distance to reach the parent plus the edge connecting the parent with the neighbor. Is that distance smaller, or the initial distance that the neighbor was storing, that is smaller? Whichever is smaller, I will consider that. Fine, and put that. If this is smaller, I will put that. That's it. And then I simply return later. Once this whole algorithm finishes, we will return. So that's the idea. Now, so follow the highlighted part of the code, that is basically the current line which is under execution, and you would get to see the variables which come below, right? You would see, let me do it in another way, that would be better. Oh, it's already there. Fine. So just a second now. Yeah. So let's start from here. So please see this panel, huh? On the left hand side, you would see this panel. Yeah, this local variable, special variables, right? Just see what are the variable values at that point when you are at a particular line of code. Okay. So see that D edges that you can see over here, that D edges has come because that line is executed. Size is 7, that has come. The list initialization has come. Now see, please see the value of I. Acha, at first, are these text visible on the left hand side, the variable values? Can you all see that?
Yes, sir.
Okay, fine. Fine. So what are we doing here? We are just initializing the W list, right? To send it to the Dijkstra algorithm. We are initializing it. How we are initializing it? For each of the, in this tuple, right? For each of the tuple over here, sorry, in this list of tuple, for each of the tuple, this tuple means there is a vertex, there is an edge from vertex 0 to vertex 1 whose length is 10. So what are we trying to do in these 3-4 lines? Is we will set the first vertex as the key of the dictionary, all the tuples, right? 0, 0, 1, these all would be your key. And then we will simply add the distance and the second vertex as the, we will append that, right? We would append that there is an edge from 0 to 1 whose length is 10. So the key would be 0, 1, 2, 3, 4. How many vertices are there? So here currently we have 5. So that would be the key. And here currently we have up to 6. So 6, that would be the key. And 0, 1, 2, 3, 4, 5, 6. And the values would be again a tuple. The value would be a tuple. You see that this is the value, right? For each of the key, which is 0 to 6, that we have a tuple as the, we have multiple tuples as the value, where each of the tuple represent the edge from the key to that particular vertex. So let's say if I say JD, so this means for the key I, for the vertex I, we have an edge connecting I and J, and whose length is D, and in I, corresponding to the key I have a list, and in that list all the tuples, and in that list we have tuples in this form, where each of the tuple means this is the vertex to which an edge from I to I is connecting, and this is the length of that edge. Fine. You can see the left hand side to see what values it actually iterates through. Fine, I would do a bit quicker. If you want to pause, if you want to ask something, please ask. See, you see what's happening? The weighting in the WL, we are actually see now 0 and 1 is there because I is 1. When I would be 2, 2 and the corresponding list would be added in WL in the next step. See, I is 2. See what happens in the next step. So 2 is added, right? A list corresponding to 2. Accordingly, we would do it. I'm just going fast. So for 3, 4, 5 and 6. Fine. After that, what would happen? We have actually created all the list. Now we have to append the corresponding edges. So now you would get to see the values. Right? See, now we have a value over here. If I just see over here, the value 0 corresponding to 0, 1 and 10 is added. So that means there is an edge from 0 to 1 whose length is 10. Got it? So if I just do it again and again, you would see that each of the edge is added. So now second edge corresponding to 0 is added. So from 0 to 2, there is an edge whose value is 80. Okay, let me just make it a I can't reduce it much. Okay. Anyways. See now for 2, 370 is added. Like this, we are actually creating the adjacency list. I hope you all can see the highlight that's happening on the left hand side. See now D5 and J6 is highlighted, right? Because J is the current vertex to which it is going and D is the length of that edge connecting, right? Since the code is working on J, D and I, you would see that these values are the highlighted values. Okay. So now 4 to 6 is added. Oh, sorry, I clicked once. Set a breakpoint over here as well. Okay. You are getting what's happening. We are now trying to calculate the infinity in the next step. What is the infinity value? How would we calculate that? Right. So I'm not explaining how the infinity is getting calculated. You all can check that because see infinity value is 561. So why I did have to click it multiple times, because this is essentially a loop, right, which is running there. This is a nested loop. So that has to run. That's why for each and every iteration, I actually had to click it to proceed it one step by step, and that's how it calculated the value 561. So the value is 561. That means what? And since this is not directly related to Dijkstra, I'm just asking this. This means that the maximum length of any edge which is there in the graph, that multiplied by the number of vertices, which is 6 in our case, right? Sorry, 0 to 6. That means 7 in our place. So 7 into some number, that some number is actually the highest weighted edge on the graph, plus 1 is actually 561. Right? So simply you can minus 1, so that is 560, and divide by the number of edges, which is 7, right? So if you 560 divided by 7 is 80. So we can understand that 80 is the highest weighted edge on the graph. If you just check that from the data, you can see that, yeah, that is correct. 80 is the highest weighted edge. Okay, so let's proceed. So,
No, but
yeah,
we could also keep it as like 81.
yeah, anything. Only thing that no 81. See, why not 81? Because here you are not doing spanning tree. spanning tree, you would only add the edges. You are not worried about the path length. You would only see where the current edge is lesser than the
Got
greater
it,
than
sir.
the
Got
correct.
it, sir.
But here you
Yes.
are taking the path.
Cumulative. Here it is cumulative. Yes, sir.
Yeah. So if you take 81, so at some point the path length would be obviously greater than 81, right? Because 2, 3, 4 edges would be there. So once it
Yes,
becomes
sir.
greater than 81, your conditions would not work properly. So that's why, that is the reason we are multiplying the highest weighted edge with the number of vertices. So if I do that, what is the guarantee that I get? So let's say there are n vertices. How many maximum edges are required to connect n
Path
vertices?
will always be lesser than that infinity.
Exactly. And the idea behind that is, if I need to connect n edges, n vertices, then I would need n minus 1 edges, right, in order to connect them. So if I need n minus 1 edges to connect these n vertices, and I simply multiply the maximum weighted edge that can be there in the graph. So with the number of vertices, or minus 1 also, there is no problem with that, or with the number of vertices. If you multiply that, then that is essentially giving me an upper bound on any possible path in the graph. And we are just doing plus 1 to be a bit more, what should I say, more strict or more conservative. That's it. That is the idea. So actually there was a discourse post on this, that why we are going through the hassle of calculating all this thing. We can just take infinity, the macros that are defined in a language, to take infinity. Let me tell you one thing. There was a very important YouTube error once in 2019, I suppose. I'm not sure about that, which had to do with this selecting of maximum value. So the developer who wrote the module corresponding to that part, he used a data type. I don't remember which language he used, or whatever the data type was, but the data type he used in order to define the maximum macro available for that data type. Correct. So that had a limit. The data type has a specific limit, like 8, whatever, maybe it's 8 bytes or 4 bytes, whatever. Now, that the maximum value within that data type he used as the maximum limit. But once I don't know what was, I'm not totally remember what is the specifics of that issue, but I think it was related to views or likes or something. But once the views exceeded that maximum value, it was actually getting rolled over. So that happens whenever the maximum limit is exhausted. The whole count actually rolls over from 0, sometimes from negative also, if it is a signed number, right? So then it is totally illogical. Let's say the YouTube views goes beyond 1 million, it gets to 1,000,001 is not there, so it becomes -1 or something like that. So the idea is, the thing that I want to discuss is, see, macros are good, but you should be totally aware of the system beneath that macro. When you are using some predefined macros or function or whatever, and you are really writing a you are really developing an important software, or not as project, but as your employment or something, some important thing. You should be very much aware of the underlying process, how that language is dealing with that, because there can be intricacies corresponding to your program or use case that may fail, right? So but when you are logically defining something, see, in whichever language I go, whatever be the use case, this would not fail, because my infinity selection is based on the test case itself. Unless whatever test case you give, my infinity would be greater than that, right? If I use this logic, I am totally independent of the language, I am totally independent of the system, I am totally independent of the use case or the test case, right? So logical initialization of negative and positive infinity is what is more encouraged while you will go for interviews. And this is something they would point out sometimes, that what happens if this is the case. Fine. Can you define a metric of defining the infinity in your program? So these things are asked. So this is a good practice. That's why sir has discussed that. I have personally faced this question. That's why I'm totally aware of it. That they will ask you that in mostly algorithm based question, that why you are defining, what is the logic of defining infinity? Why you can be sure of defining it, that it would be always greater than something in your algorithm?
Basically, something which is unreachable.
Exactly. Fine. So let's proceed. we have done this far. The initialization, I'm just going a bit fast. Five, six. Okay. See, so we have initialized everything as false, and now we would do the start vertex, and now the game starts. Okay. See, the distance of all the vertices are 561. Correct. Only the first vertex is 0 because that's what we have done in this line, line number 7. Correct. Distance of all vertices are 561. You see the data. And that's why my 0 vertex is popped out and put into next D. Once I click the next step, it would pop out my 0 vertex, right? So if you check the next D, it is 0 over here. Correct. Why? Because the minimum distance, I mean, sorry, not the minimum, the distance which is the least in this distance dictionary, right? It is 0 has the minimum distance, 0 vertex, which is essentially 0. All other has 561. That is the basically the infinity. Fine. Now, once we proceed like this, 0 is taken out, but we just discussed that the list is empty, right? Only 0 would be there in the list because there are no other nodes which has the same distance. So you see next V list, my cursor is there. Only 0 is there in the list, right? So let's proceed now. We set the visited of 0 to be true. So you see this visited now. Once I click the next step, the 0 visited would be true. See, right? 0 visited is true. All other are false. And then we are checking for the neighbors. I mean, for each of the neighbor, we will actually check the non-visited neighbors and their distances. Fine. But simple thing, just you go to the distance tab and see, now I change the value of 1 to 10. Why? Because there is an edge from 0 to 1 whose value is 10. Correct? So, and obviously 10 is lesser than 561. Initially this was 561, right? So 10 is lesser than 561. So accordingly we modify that. And then you continue this step for all the vertices. So do we have any other edge from 0 connecting any other edge? Sorry, connecting any other vertices? Yes, we have 0, 2, which is 80, right? So 80 is again lesser than 561. So if I press next, what will happen? The value for 2 over here would be changed from 561 to 80. See, right? Value of 2 is changed from 561 to 80. And I don't think there are any other edges from 0. So yeah, we don't have any other edge. So now you would see that my this highlighted 16 line, my interpreter is at line number 16. Now we would again go back to this line, the first line, right? Line number 10 when I press next, because all the vertices from 0, starting from 0 has exhausted. See, we just came at line number, I mean in the start. Now we would again do the same process. Now 0 is done. So 0 is true, right? See, visited of 0 is true. So now we would start from the next value, which is 1. For u in wlist.keys, that means next is 1, right? So wlist is 0, then 1 is there. So we would start from 1 and proceed in similar manner. Okay, so I would not do the whole thing again. Same process. Any doubt, please ask. Okay, so no doubt, I'm assuming. Now I want to discuss before going to the improvement on Dijkstra. So let me just point out two important things and then we would go to the heap part of it. See, so what are you doing in this whole algorithm? This part, just focus on this part. So the time taken by this algorithm is n square. Okay, I'm not going into the details why it is n square. You should have seen that in the video. Now the reason is, see, obviously you are going into you are calculating this minimum and you are, I mean, you are also checking in this list for all the edges whether the current distance is lesser than the, I mean, this term, right? This value. So you're checking that for all the edges and you are doing that for each of the vertex, right? So, and also this part, this calculating of minimum is again something which is taking you order of n time, and you are doing that for again all the vertices. So basically this takes you order of n squared time, given that n is the number of vertices. And that's why we want to improve it. Now, how we can improve it? What are the main tasks that we are doing? So this is the main task, and finding the minimum from the set of current distance is the second important task. So this part. So line number 10. Okay, this is just a, I mean, it's a bookkeeping kind of work, right? That is there any other value corresponding to that minimum value? Is there any other vertex corresponding to that minimum vertex, correct? So, but this is the logically this part, line number 10, and this loop, for loop, line number 16, 17, 18. This is which is the most important core of the algorithm. So we have to somehow see what is the operation that we are doing. We are actually finding the minimum in line 10, and in line 16, 17, and 17, 18, we are checking if the minimum, we compare between these two values and then change the value depending upon distance v. We are depending upon whichever is minimum, we change it. So we are changing the value, and we are also using the same value. See, both of these are distances. We are also using the same value to find the minimum. Now, what have we learned in heap? Heap actually is good in finding the minimum, and we just compared in yesterday's session that when you have to change the value, when you have to insert or update values, right, then heap is better. Otherwise, if you only have to find minimum multiple times and you do not have to change the same data again and again, observe here I am changing the distance itself whenever minimum is satisfying. Okay, and here I am not changing distance, I am only calculating which is the minimum distance. So here we are finding minimum, here we are changing the same value whose minimum we are finding. So when you have this search, finding minimum along with modifying the minimum, so these two things when happens in parallel in an algorithm, you should go for heap. That's the indication you should use heap. Okay, if the minimum finding is there, but multiple times you do not have to change the value, then sorted array is better. Now I am assuming that you all have gone through the theory part of the algorithms, and if not, please go through it and then again revisit the session. Out of Prim's algorithm and Kruskal algorithm, we would go through that, but before going to that, out of Prim's algorithm and Kruskal algorithms, where we would use array and where we would use heap. I don't need the answer, I need the reason. The reason is, in Prim's what happens? You put all the values in a place, you find the minimum, and then again check whether the current age is lesser and then change the value, right? We would go through the code of Prim's again, don't worry, but I'm just stating it. Okay, so there also in Prim's also what you do is you check for minimum and you modify the value, after which you again check for minimum. So modification and checking for minimum happens in parallel. So again Prim's is a candidate for heap. But in Kruskal you do not do anything, you simply pick the minimum edges one by one and add it unless and until it forms a cycle. Fine, you do not have to change anything, you are not changing anything. So that's why Kruskal is an candidate for normal sorted arrays. So you see, you can simply sort it. That's what we do in Kruskal. We simply sort the edges and then we add one by one. Now that adding can be done in a brute force normal way, or you can also use the union find data structure. That is a separate story, right? But finding the minimum in Kruskal, we use an array because we do not modify the data corresponding to the edges. In Prim's, we find the minimum edges as well as we modify the data corresponding to the minimum edges. That's why we use heap. In Dijkstra also, here we are finding the minimum edge by checking on distance. Here we are modifying the distance. That's why heap is better. Because if you have an array where you are storing the distance, correct? If you like this, like in this case, this is just a dictionary, right? But that's what I'm telling. If you use a sorted array, while you, in this case, to change the distance v, right? So it would take order n time, correct? You have to shift all the elements and do that, all those things. But if you want to change, if you want to only take minimum, it would take order one time in a sorted array. So the next improvement that we want to achieve is by using a heap in the Dijkstra algorithm. Okay, so we would go to that code. One last time I am asking, is there any doubt in Dijkstra, this basic Dijkstra? Okay. So stop it. So this is my Dijkstra with heap. Okay, let's see now what happens. Okay, before going to Dijkstra with heap, at first we would also have to discuss how the code of heap works. Okay, so I would now set it over here. Okay, so before going to this part of the code, I would at first like to discuss some basic properties of heap again, not in, I mean, from the coding point of view. Okay, so just a second. Okay, see, so there are mainly, I would just revise this a little bit. So in heap, what we learned is while creating a heap, what are the steps that we do? So let's say, okay, I would go very fast. Okay, if you have not seen the lecture
Parent
yesterday,
child.
correct. Okay, so if this is my I mean, this is my, okay, so let's say, okay, so this is my heap. Not heap, this is a basically a given array. Now I discussed with all of you, right? So how to represent this in terms of array. So simply 2 6 1 10 20 dot 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 whatever in the sequence you do that. That's basically representation of heap in the form of an array. Now the reason is, if I is my parent's index, right, you would see the exact same thing we discussed, and that's the code. Then 2i plus 1 is my left child, and 2i plus 2 is the index of my right child. You apply it on any one of them, see that this would work, right? So if you take this element 10 and see if 10's index is 0 1 2 3, right? So if I apply it over here, so 7 is the left child of 10, the index 7, and 8 is the right child of 10, index I mean the index 7 and index 8. So what is index 7? 0 1 2 3 4 5 6 7. So 50 and 36 are the children of node 10. See, okay. And the logic behind this idea also I discussed. So okay, so this is the representation, but obviously this is not a heap. Structurally this is a heap because I have filled the element from top to bottom and from left side to right side, right? I have not bypassed that rule, but logically the analytical condition I have not actually followed, right? The parent must be greater than the children, or if it is a min heap, parent must be smaller. That condition we have not followed. So let's say we are going for min heap now, since min heap is what we would require in all these algorithms. So min heap is what we are going to make. So the topmost element should be the least element. So what is the process? I will not go through the whole process. Just I'm just revising what we would do to make this heap. What we would do is we would start the process from the first non-leaf node. Okay, because where you have to check whether parent is greater than the child, correct? So where you would have to get a parent first. So what is the first parent from the bottom in this list? You know that whenever we do some operation on the heap, it's better to do from the bottom so that you can get the whole span of the heap, right? You can work on the whole span one by one. So you have to get the first parent from the bottom. So who is the first parent? This is not a parent. This is not a parent. Neither this, nor this, nor this. 10 is the first parent, right? 10 is the first parent node. So how can you actually get this parent? There is also again a logic behind that, right? I can see from the heap it is 10, node 10. But logically, how can you understand that from where the parent nodes start? So if you follow, that's why this property of heap from top to bottom and left to bottom, that comes to your rescue. So if you follow this property, you actually end up with a almost complete binary tree. And that's a heap, right? We discussed. Now, if it is an almost complete binary tree, I also discussed with you half of the nodes, total number of nodes in the heap, half of them would reside at the leaf level, and half of them would be internal nodes. So if that is the case, I can tell that the index half, I mean, if n nodes are there, then the index half n by 2 minus 1 or n by 2, we would check that. So that would be my first parent, correct? Because half of them are leaf nodes. So how many nodes are there? Let's try that. How many nodes are here? 4, 5, 6, 7, 8, 9, right? 9 nodes are there. So if I do 9 by 2, we get 4, correct? If I do 9 minus 1 by 2 also, we get 4. Okay, so what is the index? 0, 1, 2, 3. So 3 is the correct answer, correct? So I think then it is 9 by 2 minus 1. The last, yeah, 9 by 2 is half of them are from the leaf, right? Correct. Half of them are from the leaf. So before that, right? So this is the, if you apply that, let's try that on any other heap as well. So let's do this. If we have a heap like this, what do we get? Right? 0, 1, 2, 3. So there are 4 nodes. So 2 minus 1 is the first parent. So you see 1 is the first parent. 4 by 2 minus 1. So 2 minus 1 is 1. So 1 is the index of the first parent. So this is the first parent. Got it? So that's the idea. The main logic is minus 1 plus 1. This boundary adjustment you have to check. But anyways, so the logic is half of the nodes are always there as the leaf node. Half of the total number of nodes in a heap, right? Because it's an almost complete binary tree. So you can get the index of the first parent by applying this formula. Given n are the total number of nodes in the heap, simply do n by 2 minus 1. You would get the answer, right? And I think this is floor, right? So whatever this is my first parent node. So from this node, I would run a loop for whatever this value is. Let's indicate it I. So I would run a loop that would start from, okay, I'm just writing the pseudocode, then I would go to that. So that would run from my index I, corresponding I is equal to this, the first parent node, and then it would go, it would go to the next parent, right? So how would we do that? We would check. But before going to the next parent, what is the task that we did? We have to check whether this part, right, this parent and the child, whether they follow the heap property or not. So we simply find who is greater. We are finding min heap, right? So we simply find which is the minimum value. We put that in place of the 10, right? So we get minus 36 is the minimum value. So we simply replace 10 with minus 36. And here we put 10. Okay. And then again we would check for the, so this is done. This much part is done. So then again my for loop would actually go to the next parent, right? The next value. And then it would again check for the whether the heap is following the property or not. So it would go to 1 and then it would check. Fine, this thing. Okay. So it goes to 1 and checks whether the properties are followed. So property is not followed. This should be minus 12 over here and 1 should be over here. Fine. And then again it goes to the next parent over here. Now when it goes to this parent, so it would check for this part at first, that is correct. But see, if I do a swapping, like in this case, it would happen, right? Minus 36 is smaller. So I would do a swapping over here and 6 would come at the bottom, right? 6 would come here. Now, since I have done a swapping, correct, I may have disrupted the heap below it. Correct, I don't know. I may or may not. So that's why I again have to call Heapify over here. So whenever you do swapping, you again call Heapify, remember, recursively. So you would do that. So although this may sound a bit difficult, the only thing you have to do is from I to your root node, I is equal to this. I'm telling this is not generic I. This starts from here, from the first parent to your root, which is 0 basically. You only have to call Heapify on I. That's it. Done. Okay, That's your code for creating the heap. And Heapify algorithm I have discussed in the last class. Those of you have seen it, nice. Those of you are not, please see that once. I would not go into discussion of Heapify today. So that's the only thing that you have to do. All other things Heapify would take care of, right? So if you do it for, I mean, if you do this for all the vertices from all the parent vertices, then you would end up with a proper heap. Fine. So yeah, so here it was 10, right? 1036. So anyway, this we know we don't need any swap over here. So this is fine. And so finally 2 is left. So we would call Heapify on 2 and check which is the minimum value. 2 is not, minus 36 goes over here. 2 comes over here. And 2 is actually satisfying 20 and 6. Fine. So basically you got a minimum heap. So this is the steps. So let's go to the code and check that. This is basically the Heapify algorithm that I was telling. And I think this is the same thing that I just discussed in pseudocode. Yeah, you want to say something?
Sir, can you explain that part again? Like, why did we had n by 2?
Why?
N by 2.
Yeah. See, if you do it trivially, right? This is satisfying, isn't it? Just by experimentation, trial and error. Is it satisfying? See, here how many nodes are there in this structure? 4, right? So if
Yes, sir, 4.
if I do 4 by 2 minus 1, at first let me confirm that. I also half would be there, but it is n by 2 minus 1, right? Size by 2 minus 1. Okay. Yeah. So always these things, keep the basic logic in mind, and some boundary condition check you have to check whether it is minus 1 plus 1. Okay. So those things. Yeah. The logic is, see, n by 2 minus 1, 4 by 2 minus 1 is giving me 1. So if I check the first parent node, right, then its index should be 1. So is it satisfying over here? See, 0 is the first index, 1 is over here, right? So this is array, right? I told you this is just an array. Okay, where did I draw that? Here, right? 2 6, this is just an array. Indexing, normal list or array, whatever you want to say. So this is just an array which is represented in the form of a heap. Why it is represented in this form of a heap? Because if you, that's what I told, if you take any particular node 8, what is the index of 8? 0 1 2 3 4 5, right? If you put 2 into 5, if consider this as I, if you do 2i plus 1, whatever index you get as a result over here, that is the left child of 8, and whatever result you get over here, that is the right child of 8. Okay, so this is the array representation of a heap. Simply put all the values one by one, you would get the array representation of the heap. And on that I am talking, on that index I am talking. So if this is your heap, then this is the first, right? So this is basically the first element of your array. So 0. Then this is 1. This is 2. Index. I'm talking about index. Okay, this is 0 index, 1 index, 2 index, 3 index. In this, if I put, I get this 1 is the first parent by this formula, n by 2 minus 1. And obviously that is satisfying because 1 is the first parent node. Why for 1 is the first parent node? You go from bottom to top. Check what is the index of the first parent node that you encounter. Is 3 is a parent node? No, because 3 is leaf node. It has no children. 2 is not also a parent node because it has no children. 1 is a parent node because it has 3 as a children. So that's why, I mean, this node is the correct index that we got. 1 is the correct answer. So same thing we did over here in this as well, in this case, right? Here, how many vertices are there? 7, 8, right? 8 vertices are there. So if I do 8 by 2 minus 1, what is the result? 3, right? So if so my third vertex is basically the third index vertex is the first parent node that I would get. That's the idea. So if I do 0, 1, 2, 3, correct? So if I see, these all are leaf vertices. This is the first parent vertex. So that is satisfying. So the formula is correct. Now the logic behind the formula is, since this is a binary tree, and it's an almost complete binary tree, what is the condition? If there is one node, I will have 2 nodes at the bottom. For each node, I can create 2 nodes. So what are you essentially doing is you are doubling it up. At each level, you are doubling up. So at each level, if you double up, then if I say there are total, let's say dot, 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 okay. And here are, let's say some nodes are there. Okay. And if I say this total number of nodes are n, since it's an almost complete binary tree, at each level you are multiplying the previous level by 2. So it is 2 to the power 0, it is 2 to the power 0 into 2, that is you are doubling it up, whatever was there in the previous level. Then it is 2 to the power 0 into 2 into 2, because this was there in your previous level, correct? 4. So you are doubling it up. So if there are total n nodes, so obviously till the last level, it must have been n by 2. And that's why you double it up in the last level. So you n by 2 into 2, you get n. And that's why you got n as the total number of nodes. Concept clear? That's why I said that half of the nodes of a heap must be there as a leaf node, and all the intermediate nodes only create the other n by 2. And only the leaf creates n by 2. And not only in heap, this happens in all the almost complete binary tree or complete binary tree. This would happen. Fine. And that's why our idea is if n by 2 leaf nodes are there, then that means n by 2 minus 1 is the first parent node from bottom. Is it clear?
Sir, finally we took n by 2 into 2 because at the last level, pre-final level, we will have n by 2 nodes.
Yeah. Every level you are doubling. Total number of nodes n. So that means obviously the last level would have been n by 2, and if you are doubling, that's why n by 2 into 2 is n. Right. So that's the idea. Fine. Okay, so I discussed that in detail because now these code should be very easy for you, and we can move very fast about it. So say Heapify algorithm, the pseudocode I discussed, you can also check the session and then simply just write this function. It's exactly the same code that I discussed, the pseudocode. So you have the left child, right child, right? And you check any. So in this case, I took an example with large heap, sorry, max heap, right? So I took a greatest variable to store which is the greatest value of the 3. So here we are using min heap. So we are taking a small variable to store the value which is minimum, right? In this process, in this process of whatever we discussed, right? We in this subtree, we were checking which is minimum, right? Out of these 3, whether the left child is minimum, whether the right child is minimum, or the parent is minimum. So same step we are doing over here. Same step we are doing, left child, right child, and we are storing the minimum in the parent if left child is less than h2v and v2h. Okay, so this is what, see, whenever we are creating the heap, whenever we are creating the heap, suppose what I mean is, okay, so in Python, did you all learn heap? It's very difficult otherwise. Or tree, at least any tree data structure, did you all learn? Or in CT, some basic tree or heap or anything?
No, sir.
Okay.
Actually, don't remember.
The problem is here you all have to learn algorithms as well as the data structure from scratch. So that is something is difficult. Okay. Anyways, so basically what we are doing is, since it is a heap, let's take that, let's say 10, a min heap, right? So 24. Okay, this should be fine. So this is a min heap. Okay, let's add one more, 18. Oh. This is a min heap. Okay. Now, obviously we discussed about the extract min part. So you can extract the 10 value from here. So that is a good property of min heap in a log_n type, right? Why log_n? All this thing we discussed. Please check the previous session. So in log_n time, you can take 10 out and put 48 in place of 10 and do whatever we discussed, right? But if I ask you, what is the time taken to search an element in a heap? If I tell you search the value of 36, search 36, where is 36? I mean the index. I need the answer as index. What is the index of 36? Okay, in a heap. How much time would you need? Okay, I mean in terms of worst case, tell me in terms of order of n, L, log n, whatever it is. What is the worst case time that you would see?
Log in.
Why log n?
Log in, sir.
Okay, please tell me the approach that you would go through.
Because the height of the tree is log n.
Okay, then you have to take the approach, right? Every answer cannot be height of the tree is log n. What is the approach? See, when we are doing delete minimum, delete minimum, extract minimum, whatever you want to say. So that means we are taking 10 out. What was the thing that we were doing? We are taking 10 out. The space was getting empty. That's why we were putting 48 in place of it. Swap 48 over here, the last element I mean. Okay. Now once that is done, what you do? You call Heapify on 48. You call Heapify on 48. So Heapify means what? It would check whether these three are your, I mean, the smallest value, that same thing. Then if there is a swap, then that swap would, let's assume that there we will do a swap. So not assume, actually here that would happen. 24 and 48 would swap. So once 48 comes over here, then I would again call Heapify over here. Right? So that's how Heapify works. So if Heapify works like that, that is the reason it is log n, because I have to reach the root, leaf node. Correct. I have to reach the leaf node. I forgot whatever value was here, but 28. Yeah. Okay. So basically you are going one by one level by one like this, and that's why we used to discuss that it is log n time. But if I tell you search, you at first tell me what is the step that you would do in order to search 36. You come over here. This is the root node, right? Root of the heap. So this is the only location that you can access. After this, what will you do?
Compare the value of the root node with 36.
Sorry, can you be a bit louder?
Compare the value at root node with 36.
With the child, right? Left child, right child, or only one child?
Left child and right child, then we see which side to move.
No, I'm not telling you to move anything. I just want the index of 36. So you compare 24 with 28. You compare this key 36, right? You compare this key 36 with 24. See, it's not same. Then you check 36 with 28. It's not same. Then you get 36 with 36. It's same. Now you return the index is 2. Okay, 0, 1, 2. Okay, if I need the index of 48, what would be your step? You have to, there is no way, you have to check all the nodes, because the reason is you have no relation between the siblings. I cannot decide by seeing this value. In binary search, what we did, we know that the least elements are here, and as we move right side, we get greater elements, right? So at any point, if I'm checking over here, I mean, I'm checking key equal to this value or not, right? This value or not. And if I see that the key is greater, that means the value over here is a smaller value and my key is greater than that. So we can decide that I have to move right side. And that's why you got log n time in binary search. Fine. Because you were actually able to eradicate this half part. You did not have to check that. So you can take a decision because there is some relation between the data, and that relation is it's in ascending order. But in heap, the only relation is between parent and child. Okay. And when I'm saying that you have to search 36, right? You check that 24 is lesser than 36. So the only conclusion that you can draw from checking 24 and 36 is that since 36, the key is greater than 24, and I am working on a minimum heap, that means 36 should be below 24. That's the only conclusion that you can draw while comparing 24 and 36. And that is quite trivial, because if 24 is my root node, obviously 36 is below 24. So I am not being able to draw any intelligent conclusion using which I can reduce my time. Right? If I compare 36 with 28, right? In the next step, can I say that I did not have to move right side, or I can move left side or the other way? No, because there is no relation between 28 and 36. Correct. That's why in heap I have to search all the nodes if I have to search an arbitrary element. There is no way you can find that. Yeah.
There's a big of n.
Big of n. Correct. So the search time of an element in heap is order of n. Now that's a problem, right? That's a problem, because if I want to extract an element, it's log n. If I want to insert an element, it's log n. If I want to change a given element means I want to change this 36 to suppose any value. Let's say 12. I want to change 36 to 12. Fine. What will I do? When I say I want to change 36, that means the change function which is there. Please pay your attention over here, because once we move to the code, you would exactly encounter these things. Fine, and I would just fast say those things in a hurry and then move out. Huh? So please see these things. When I'm saying I want to change the value of 36, what I would have to give to this function, I have to give the index. If I want to do it fast, index of 36. So index of 36, if I give it to be 2, then obviously it's, since this is an array representation, right? So I can simply go and let's say this is the array corresponding, this is the basically the heap, not the. So let's say this is the heap H. Fine, and that is actually a array representation only. So what I do is, in the change function, I would do H of 2. At first I would make it 12. Fine, and then what I have to do, if I make it 12, if I make this value 12, what is the next thing that I have to do? I may have disrupted the heap, right? So
we'll
again,
call Heapify.
correct, Heapify. Actually, we have to see what we are doing. So this change is actually there. See, nice point. So there can be two possibilities. Either you are increasing the value or you are decreasing the value. So if this is a min heap and you are decreasing the value, right? And now I just decrease the value from, it was, what was the value? 36, right? Yeah. So I decreased from 36 to 12. This is a min heap, right? So when I decrease the value, I am sure if any change happens, since I have decreased, I would obviously go on the top, right? I would go upwards. So sir has explained this in the lecture. If in a minimum heap, I am changing the value, the initial value of any node to, I mean, the change is negative. The changes I'm decreasing from the previous value. That means all the value which were below, so let's say 48 is now below, right? The below it's a child of the changed value. So there would be no problem with 48, because if I'm decreasing, I know that all the value which are below, they are already smaller than the previous value, and now I have decreased it more. So obviously it would be the parent would be obviously now much more smaller. So minimum heap, no problem. So all the children would be safe. I do not have to make any changes there. Only change is if I have reduced this value much more, right? Then this node's current parent might be greater, which is actually this case, right? 36 was there, 48 was its child. I made 36, I reduced 36 to 12. 48 would not have any problem, but 24 has a problem. 24, I must put the 12 in place of 24 and place 24 in place of 12. Correct. So in a min heap, if change is decreasing, so now I define two functions, change decrease and change increase. Therefore, in a heap, this change you have to form two different functions depending upon whatever heap you are working on, min heap or max heap, right? So if I do a change increase and change decrease, now let's see what we have to do. Why I differentiated it into two different functions. The reason is, in a min heap, I am saying it again and again, because once you go for max heap, the logic just changes, right? It becomes just the opposite. So in a min heap, when you are decreasing, only change can happen is the decreased value can go up, right? And that's why obviously I would do the change. I would do h2 equal to 12. And then I would not call Heapify. Heapify works on subtree, remember? Whenever I call Heapify, I have to call Heapify on the root, and it checks like this. Heapify is called on this node, right? But I do not have to. So what is essentially, if this is calling Heapify, then I am checking these nodes, but I do not have to check 48 now. I only have to check whether the top is correct. So I would not call Heapify, rather I would just simply do the insertion. Remember when we insert a new element in a heap? So if this is a heap, if I insert, let's say this element over here, this is a new element. What we used to do, we used to check this element with this element, if it is placer or not, and this element with this element, unless and until we go till the root. So that's what we would do. We would simply run a for loop and check whether the parent, how can I get the parent? I just told you, you get 2i plus 1 and 2i plus 2 given I is equal to parent. This is your left child, this is your right child, right? So if I simply divide any index value by 2, I would get parent. Take an example, 0, 1, 2, 3, 4. I'm saying things much faster because otherwise we cannot complete it. I would request, if you are missing something, please rewatch it on YouTube. 0, 1, 2, 3, 4 is there, right? If I say who is the parent of 4, if I want to get the value, the index, who is the parent of 4, right? What can I do? I can do 4 minus 1 by 2. What I get? It's 1, right? 4 minus 1 is 3, divided by 2 is 1.5, that is integer value 1. Let's apply it on 3. Who is the parent of the index 3 node? So 3 minus 1 by 2, what I get? 1. Correct? So again 1. Let's apply it on 1. Oh, it's anyway 0. So if I do it for one more iteration, this is 5th index, this is 6th index. So if I do 5 minus 1 by 2, it's 2. See, 2 is the parent. So what you are doing, you would simply write a loop, and that would start from this index, right? Index by 2 to 0, the root node. Okay, and you simply write if my value, whatever the value is, I mean this h of index. Okay, this is also h of index. I just, since it is 2, I took that example. This is also h of index. In code, you would write that. So h of index is greater than h of formula, this one, index minus 1 by 2. Sorry, not greater than, it's a min heap, right? So min heap, then you simply swap these two. That's it. So this is your change decrease. Now what would happen in change increase? Same step, I would do h of index equal to the value 12, then Heapify. Now Heapify, why? See, if I increase the value, if I make it from, it was 36, right? So I make it from 36 to 48, or let's say 50. I increase the value from 36 to 50. Now I'm sure that since the min heap and I've increased the value, I do not have to go on the top, because top is all smaller values. Only thing is, I may have disrupted the heap in its bottom. That is, I may have increased the value so much that any child node is actually now smaller than myself. And that is what's happening. 48 is smaller than 50, but it was greater than 36 initially. So now I would call Heapify on 50. Okay. So let me delete this. Heapify on index. Yeah. That's it. So see, I mean, if you try to remember all these things, you would never be able to remember all these things. Just try to figure out in the drawing, in the theory part. In PDSA, theory is very important. If you can think of the steps that you would take in order to create the heap, in order to insert anything, then obviously you can translate it into code. It would take time to code the thing, but obviously you can translate it. Fine. So there, in a min heap, I am repeating, you can have either increasing the value or you can decrease the value. If you decrease the value, then you are sure that any changes that would take place, that would have to be shifted upwards if required, or it may not be required at all. But if required, I have to shift it upwards because I have decreased the value and now my parent can be greater than me. That's why I have to shift it upwards. That's why we are running a loop and just checking to the top. And if you are, other hand, if you are increasing the value, that means your child may now be disturbed. And that's why you are calling Heapify. Heapify always works on child like this. I am calling Heapify on 28 and I'm comparing 28 with its child. Okay. And this two lines that I just wrote over here for index by 220, what you are doing here, your index by 2 is the parent and you are checking one by one all the parent. That's it. Fine. And this updation should be again index by 2 by 2. I mean, the next for loop where it is running, it should be updated by index by 2 only, right? The next parent. I mean, what I mean is, so if this is a heap, I would show you in the code again, but if this is a heap, correct? And this is the node that I'm actually talking about where I did some increasing. So I would check this node, I would check this node, I would check this node, but I would not check this one, right? Right? And neither will I check this one. So if I simply, so if this is my node, obviously I would get the same formula n minus 1 by 2, right? This index, this formula, this index by 2, index minus 1 by 2. If I apply this formula, right, I would get over here in the current parent of this node, right? I would come over here. But if I then simply do range function, which is simply modifying by -1, -1, correct? So the next thing that I would compare this node with would be this node, because this is the next node, right? After this node, next node -1 would be this one, but I don't want to compare it. So my next iteration would be not by using range. You have to modify the I variable by every time you would divide by I by 2. So I equal to I by 2. If you do that, then you would check this node and then you would check this node and then you would check this node, because I by 2 means parent. Sorry, I minus 1 by 2. I'm making this mistake again and again. I minus 1 by 2, correct? So if you do this every time, you would check parent. So essentially you have to run a while loop and start from whatever the index by 2 you got, right? Index by 2, index minus 1 by 2. And then when you actually modify the index, you have to later write index equal to index minus 1 by 2 to get to the next parent. So basically you are checking these parents, not this one, because this is not the parent, correct? So I'm going to the code that would make things a bit easier. See, now you would see multiple similar expressions, just this H2V, V2H, all these things would differ. I would also explain what is that, but you see this, see H minus 1 by 2. I mean the parent, that how can you go to the parent? Okay, you run a loop over here, which while I is greater than 0, and you calculate the parent and then you just go to the top one by one. Okay. See over here, I for the range that I told you, that you start half of the elements are half of the nodes are leaf node, and that's why you start from size by 2 minus 1, right? N by 2 minus 1. See this part, n by 2 minus 1. And what you do, simply call min heapify to create the heap. Simply you do call min heapify on all the parents. Min heapify means heapify, same thing. Okay. If you want to change the value, right? Change the decrease, change decrease, and change increase we talked about. Correct? So I think min heap update. Yeah, this one. Change increase and change decrease that we talked about. So this is your min heap update. Now in the min heap here we are actually decreasing the value. Okay, in Dijkstra every time we decrease, right? If it is less, then we copy. So since we are decreasing the value, you see it's going starting from your first value, the first parent value, right? And then it goes, see, I equal to I comma size we pass as I would go to the code again, but I'm just talking in modules. Okay, so let me just see where minheap update is called in Dijkstra. So here you see you are passing the heap size and the current vertex, index of the current vertex. This is the index of the current vertex. I would explain what is V2H and H2V. But assume that the index of V is stored there in V2H. Okay, the index of the vertex V. So I'm passing the index of the vertex V over here I, and then I'm checking the parent of that vertex. Same thing, right? And then you simply check whether the parent is greater. Parent is greater, it is fine. Otherwise, you say same thing. Okay. So it would take some time to see the code, just check the code, understand the algorithm that we discussed, and then just line by line try to understand. You would see that these things are easy. The code may look a little bit more involved, but it's not like that. Okay, so H2V and V2H, what are these things? So that's why I actually first started this search idea, why heap takes order of n search. So let's discuss that a bit. Okay, so since we now know that heap would take order of n search time, you have to search all the nodes. So why not? I mean, if you have to change a particular value, right? We know that, you remember in Dijkstra, we pointed out 2 points in order to use heap, in order to implement heap within Dijkstra, in order to gain achievement, in order to decrease the time complexity. We pointed out 2 main points. One is finding the minimum from among the distance, and then is modifying the minimum. Remember, finding the minimum distance and as well as modifying the minimum distance. Now, if I want to use a heap, I would put the distances in the heap, correct? So all these nodes would be storing the distances. So I have to find the minimum. That would be very easy. That is exactly extract min of the heap. That would be order of log n time, right? That we know. But also I have to modify any value, right? We were modifying the distance parameter, correct? So modifying means essentially I have to modify any particular value within the heap. Now, obviously, if I have to modify the value, at first I have to locate the value. So let's say I tell you distance of V, this line was there, na? Distance of V equal to minimum of distance of V in Dijkstra I'm talking, or the distance of the parent vertex, the next V, whatever we call it, next V, right? The parent vertex, and this is basically the neighbor vertex. Right? Distance of next V plus the edge, that is your, I mean, I'm just writing it in this form, the next V edge, which is connecting the parent with the node, next V comma V. Okay, whichever is minimum, you would consider that and store that in distance of V. So we are basically modifying distance of V, right? So this is heap. V is there in heap. So if you are modifying it, at first I have to know what is the index of V in the heap. Otherwise, how can I get distance of V? This is not a dictionary. In heap, you have to use by writing the index. Remember, we used to write H index. Just before this we discussed, right? So you cannot write the V vertex over here like in dictionary. You have to access it using index 1, 2, 3, 4 like array. So if I have to have if I have to put index, then I must know the index of V at first. Correct? Otherwise, I cannot write like this statement. Okay. So in order to know the index, we actually maintain these 2 dictionaries, H2V and V2H. So what is this? Sir has explained this in the lecture. I'm briefly stating it. H2V means heap to vertex. Heap to vertex means what? So if I have, let's say, 20, 30, 40, 50, 28, it's a min heap, right? Okay, it's 60 only. So if I have this as the heap, V2V, what would H2V store? Not V2H. What would H2V store? It would store 20 as the key and 0 as the index. Then it would store, it's a dictionary, huh? Not a list, sorry. Then it would store 31, dot, dot, dot. Okay, 42, 53, 63, so 64. And what is V2H? This dictionary is vertex to heap. Oh, sorry, I think I just said it wrong. Just the other way, huh? Wait, just a second. I'm starting from vertex, I'm going to heap. V2H is this one, and H to V is heap to vertex. Right? So this is my vertex, and this is the index where that vertex is stored in the heap. And this is 0, what is stored? 20. 1 what is stored? 30, like that, just the other way. Now dot dot dot. Why these two are required? Because in dictionary we could do distance of v, but if I'm trying to put the distance in a heap, I need to know the index of v. I need to know the index of v, and in that index of v, I can actually put the distance. I mean, sorry, in that index of v, in that index we can put the corresponding distance value in the form of a heap. Got the idea? So these two the dictionaries we are storing just in order to keep track of the index of a particular element. And we may,
Sir, can you repeat sir, last statement?
yeah. So see, here we were using distance of v, which is basically a dictionary, correct? Now I want to implement the distances in the form of a heap. I have to put the distances in the form of a heap. And what would we gain? We would gain order of log n time for changing the value as well as for extracting the minimum, correct? That's the log n. Otherwise there we were actually getting order of n time. But the problem is, in a dictionary you can write something like this: distance of Paris, right? But in a array or a list, whatever, right? I'm talking in terms of array now, because heap, we are working here with a heap which is represented in the form of array, right? Or list also, you can take list, yeah. So array or list, can we write like this, any distance of any value? So I cannot write like this, right? I have to use indices 0, 1, 2, 3, 4. So if Paris is there corresponding to 0 index, I have to write 0 to get the value Paris. Okay, so this would fetch me the value Paris. So in list I cannot write that. In dictionary I can reference the key, right? There is a key. I can reference the key and then use that. But in list or in array we cannot do that. So I need the index corresponding to this value Paris. Okay, so in terms of Dijkstra, I need the index corresponding to this vertex V. I need the index value of that. I cannot access by knowing the name of the vertex. Okay, so I have to, if I want to modify V, so in this heap, let me just go over here. What would happen is, let me just draw the original heap. So let's say 20/A, 30/B, 40/C, 50/D, whatever. This may not be in the sorted order, huh? Let's say 30, right? So it should be greater, 31. I'm just placing normal values. So the heap that we are trying to make in Dijkstra will look like this, where A, B, C, D, E are vertices, and 20, 30, 40, 50, 31 are the current distances for that vertices. Okay, so basically I would make an array or a list of tuples or values, and that array of list, the list of the tuples basically represent heap. Okay, now whether you consider it as a list or an array, you cannot write something like let's say that this heap is named H, right? So I cannot write something like HA. Correct, I cannot reference HA like that. I have to put H0 because A is there in 0 index. Now in dictionary we could do that, here we cannot do. But since I need to have a heap, I have to use it in that, and I use it in the terms of a array or a list. I have to have the index. So where can I get the index? Here we were directly writing V by the name, but here we need the index. In case of heap, we need the index, right? Why? Because this is an array or a list, whatever. So since we need an index, we are maintaining these two bookkeeping dictionaries, where corresponding to a given value, the index of that value in the heap is stored. So if I draw V2 and H2V for this H heap, it would look like my 20 comma A is my key, right? And the index value is 0. Then 30 comma B, sorry, this B is my key and index value is 1. I'm writing it by slash just for representation. You can do it in the form of a tuple or whatever. Python tuple, anything, that depends on you, how you want to do. And here it would be just the opposite 20 comma A, 30 comma B, like that. Okay. So now what we can do, if I have to, where I was using this distance of V, in place of that, what I can write is, see this thing importantly, if I was writing distance of V, so fine. So that means I want to modify V, modify the current distance of D. Now in heap, I need to know the index. So I have the name currently, right? I have the name V. So if I have the name and I want the index, which particular dictionary I would use? I would use this, right? Because this is the name corresponding to an index. So I just use V2H of the name. Now I put the name over here, which is V, right? We put that. Now this would return me the index. I want to actually modify the H. H is the heap. Remember, H is the heap. V2H, H2V ordered dictionary. H is actually the heap. Correct? So now I would modify this H heap by writing what? H2V of that. See what's happening. V is the name. I'm using V2H to get the index of V. Let's say V in this case is the first, let's say 30 comma B. Okay. So I'm using V2H of 30 comma B. V2H of 30 comma B, I would get the result as 1. So this part is giving me 1 as the result. Correct. Okay. And now I can simply use, okay, so this is also not required. I can simply put it in the heap. Correct. Yeah. I'm already getting it. Yeah. H. So once I get the index, I can directly write H of this one. So this would boil down to H of 1. Correct. Now once I go, okay, H of 1 is accessible because it's an array list. I mean either an array or a list, whatever way you want to implement. So H of 1. So H of 1 is acceptable. So it would go over here. So how much time this process took? That considering I have the name V, I am putting V inside this part V2H, right? And then the answer, the index that I got, that index I'm putting inside H of 1, right? And this total part is actually equivalent to this distance of V. Correct. So how much time does this take? This is a dictionary. So it would give me order of 1 search time. So this is order of 1, right? And obviously there is an array, which is again indexing, and an array is again order of 1. So that is again order of 1. So I'm not losing any time. I'm just doing a bit bookkeeping work. I have to keep some extra space to do that. But just by maintaining these indices, I'm not losing any time. I'm not degrading my time complexity. Is actually order of 1 only. But now I can modify the heap directly. So now 30 comma B I go, and let's say I need to decrease the distance, right? So I on 30 comma B, that is on H comma 1. On this I call my I mean what I can do is I can decrease. I remember we change decrease, we had one discussion, change decrease function. So if I want to decrease it, what I would do is change decrease, and in that I would pass this one index, which I got from here. Okay, one index, and inside the definition of the change decrease function, I would simply remember what we did, heapify, or either heapify or simply checking the top of the parent. I mean each and every parent till the root. So depending upon you are decreasing or increasing, since here we are decreasing and it's a mean heap, so we would only check the parent, right? We discussed that. So in that, simply we would start from 30 comma B, because now we can locate 30 comma B because we have this index 1. Otherwise in a heap it would take order of n time. That's why we discussed that if I have to find this V value, what is V? I know it's 30 comma B, but if I have to find the index for 30 comma V, then I have to check all the elements, check this, then check this, like that. In the worst case, if it is 31 comma E, I have to go till here. So it's order of n time. So the finding the index by checking the value in a heap is taking me order of n time. Just in order to eradicate that, I store up this V2H and H2V dictionary, which can directly give me the index, and I put that index in the heap functions, whatever I discuss, heapify function, change decrease function. As soon as I get the index, I'm in the world of heap. I can apply it in any heap function that we discussed till now. Okay, and by maintaining this dictionary, I'm not losing any time because I just proved that this whole process, which is equivalent to this distance of v, is taking you order of 1 time. Okay, but this distance of v while decreasing, increasing, and all those things, finding the minimum was taking order of n time previously. But now, since I got the index and I'm applying the heap algorithms, I would get order of log n time. Fine. So if I do not maintain this dictionary, then again searching for 30 comma b 20 comma a, I mean searching the index for a particular value within the heap would again take order of n time. So what is the point of doing so much? What is the point of getting into so much trouble of using heap and all if you get into order of n? So just to reduce this such time of order of n, we are maintaining these two dictionary, which gives us the index. As we get the index, we put it in the heap algorithms. Fine. So that's why in the code you would see multiple times these terms h2v, v2h. It's nothing but the mapping from value to index and index to value. That's it. Okay, because searching the value in the heap, searching the index for a value in the heap would take you a lot of time. Okay, so is this concept clear? After that, we would come to the Heapify part and all those part, but basic these things are clear.
Theory is clear, sir. Code we have to check.
Yeah, code is fine. Code I would now discuss. If you understood the theory, the code is just, I mean, it would be just this, all the parts of the code we actually discussed in the theory. You would, I mean, don't you find these things familiar? This is the same thing we discussed, right? Left child, right child, smaller value, check if it is lesser, check if it is greater. If so, swap it. See, it's just swapping. It's just swapping, right? They're swapping, simple swap. So same thing. And also remember we were discussing once you swap a variable, it may go down, right? You parent you consider, left child, right child you find. Let's say left child and parent you swapped. Once you swap parent and left child, obviously the left child may now may not be a heap, right? That all the nodes below the left child may not be in heap format. So again you have to call heapify on the swapped value. So that's what we are doing. Heapify on the swapped value. Which is the swapped value? The smallest value, right? You are swapping the smallest value. So again you are calling the heapify. Remember we discussed it's a recursive function that every time it would go till the bottom. Same thing. There is nothing extra. Okay. So this is creation of the heap. This is heapify function. Again I discussed half of the node would be leaf node and all other half would be parent node. So when we are trying to create a heap, right? What was the first step that we did? Right? Remember what was the steps that we did when we are trying to create the heap? Assuming this is not a heap, this is just a normal array which is arranged in this structure. So if I have to organize it in the form of a heap, I would first find the first parent, and that I could find by n by 2 minus 1, correct? And that would be this parent. This is the first parent node. So find n by 2 minus 1. See, size n by 2 minus 1 for x in range. Up to how much? Up to the last, up to all the parents, right? So from here, this parent to this parent, then this parent, then this parent. All the parents I would go and I would call, I would check for the heap condition. So on this parent I call max heapify. Then on this parent I call max heapify. Sorry, mean heapify. Then on this parent I call mean heapify. Then on this parent I call mean heapify. Okay, same steps till last, size by 2 minus 1 to last, call mean heapify. Mean heapify we have discussed. If you are feeling a little bit difficulty in the algorithm mean heapify, please check yesterday's session. Okay, so create heap is done by these two methods. My creation of the heap is done. So create mean heap could actually call mean heapify or each of the parent node. That's the idea. That's how you create a heap. Create mean, please keep this thing in mind. I'm just repeating. This is the bottom line of the algorithm. Create mean heap would call the mean heapify on all the parent nodes of the array that you have got. Now, once you do that, you would end up with a proper mean heap. Fine. So that's done. And after that, we are basically updating the remember we discussed two methods. Either the decrease can be, either the change can be an increase or the change can be a decrease. So here that is happening. Min heap update, here we are actually doing it in the Dijkstra, right? We are doing this as a part of Dijkstra algorithm. So the change is always, this is equivalent to the change decrease that we discussed. That is, I would obviously every time I would try to decrease the distance. So this is change decrease. So we discussed that when we are decreasing the value in the heap, what would happen? In a min heap, I would only have to check the top part, not the bottom part, because I am decreasing the value. So only thing that I have to check is whether my parent is smaller than me or it has now become larger. And since I have been decreased, I have become smaller than the parent. If that is the case, I will swap the parent with myself and I would become the parent. So how many times I have to do that? I have to do that up till I reach the root node, right? Same thing, root node is while I is greater than 0, right? If that is the case, I would apply the parent equal to I minus 1 by 2. We discuss this thing, right? And then simply the condition. This H2V, V2H parent, these things are just, the data structure part of it. If you see this thing a bit quietly, you would understand. Simply H2V, you are getting the index of that value and then you are checking. Okay. So if the same condition is satisfied, then you are swapping. Okay. Otherwise, you are breaking. After that, this is delete min, the famous operation that we also discussed yesterday. You just swap that, you take the minimum element out, and then what you do? You take the last element and put it on the top, and then call Heapify. That's why here Heapify is called. Okay. Fine. What's happening over here? Check this. V2H, H2V, 0, 0, size minus 1. Here at first you are decreasing the size. That is the case. And after that, what you are doing? You are actually swapping this last value. You see this? H size minus 1 is swapped with H0. See this? H size minus 1 is swapped with H2V 0. So what does this mean? You are replacing the 0 and the last element that we discussed while calling min heap, while calling delete min or extract min, whatever you call it. So once that swap is done, after that, what you have to call? You decrease the size and simply you call min Heapify algorithm from the top, right? After putting the last node, you call min Heapify from the top, correct? So that's why this min Heapify is called with 0 index from the top. So that is delete min. So please go through the discussion. Well, when I discuss the theory part, if you want to see this session later in the YouTube, just see the theory part of a particular discussion that I was doing of a particular algorithm, and then check this code part. It would be very easy for you to understand. Fine. And once this is the whole heap operation. Whole heap operation up to here, we are doing the heap operation. So this is
delete min H size is the parameter which is passed. What is it, the total size of the heap?
Sorry, H size parameters. Yeah, that is the size, right? We are decreasing one. We are delete min was you would take out one element, so the size would decrease, and that's why we need to actually incorporate that, right? Because one element is not there in the array. It's just an array or a list, whatever you want to say. So one element would not be there. So you have taken that out. That's why we are getting the H size and then using this H size decrease by 1. Okay. So basically, before calling the next min Heapify, we are actually decreasing the H size, because what will min Heapify do? Remember, I am not going to Heapify. Remember one condition that we had to check while min Heapifying, that whether the index that I have got now, whether that is in the array at all or not. Because what I was doing, I was every time checking the parent, how much up to how much time I would check the parent, right? Or when I am going down, I was checking the child with the parent, then I was swapping and then again checking the child of that, then again checking the child of that. So up till how much I should go while checking the child, right? Up to the length of the array, correct? Because once I exhausted the length of the array, that means I have now reached at the leaf node, and I have actually also passed the leaf node. That's why my current index is now greater than the size. So to check whether your Heapify recursion has reached the level of leaf node, you used one condition in if, that whether the current index of the parent or the child as well, whether the current index of the parent and child in the Heapify algorithm is lesser than h size, is lesser than the size of the heap, then only I would proceed. If it is greater than the size of the heap, that means I have already reached the leaf node and I have already passed the leaf node. That's why my index is getting showing greater. So now let me just show that. See this thing. If L child is less than size minus 1, if R child is less than size minus 1, and then you check for greater than less than condition. Okay, so that means what? Heapify algorithm is actually using this size parameter to have a boundary condition, correct? In order to check I have reached the leaf node and now I should terminate. Otherwise, this recursion would go on and on. In Heapify, this is a recursive call, right? Self recursion. So this would go on. This is the terminating condition, these two lines. Fine. So in order to terminate that, I need this size variable of the heap. And every time I am extracting or deleting one, delete min is happening every time, my size is decreasing by 1. Right? That's why just see, before making min Heapify size minus 1, I am storing that in h size. See this thing. Just calling min heap, before calling min Heapify, I am decreasing the h size, because min Heapify will use this h size. Okay, in order to check whether I should terminate the recursion or not. Okay, so that would be delete min. So this was the heap part. Okay, delete min, min heap update. Delete min is used for deleting. Remember 2 points of Dijkstra. First is finding the minimum, delete min would serve. Next is changing the value, min heap update would serve. And these two functions are used to create the heap. Fine. These two functions will create the heap. Min heap update is the second point of Dijkstra for which we wanted the heap, that is the change in value. And delete min is the finding the minimum value. Okay, so these are the utilities. Now this is Dijkstra. Only this much. I'm not going into these parts. These are the same thing. Okay, you initialize something, initialize the variables. Then now you have to use the v2h and h2v, right? So you do some basic initialization, v infinity false, normal things, and then you call the create heap method to create the heap. So this part is just creating the heap. This is the core Dijkstra part. Okay, so now how we are using the heap. Okay, let me just compare the other one here, which was the normal Dijkstra. Okay, so this is Dijkstra with heap, and this is Dijkstra without heap. Okay, so what was the first step? Finding the minimum, right? Order of n time. In case of heap, I can get in log n time. What is the function I would use? Extract min or delete min, right? So for u in wlist.keys, I can use delete min, and that would be order log n time. This is order n time. See over here. For u in wlist.keys, delete min. Okay, order log n time you are getting same thing. Just I'm just comparing both of them, huh? So in this loop, we are using delete min to get the minimum value, and here we are using the where did it go? Yeah, where we are simply using the order n time minimum checking. Okay, so what is the next step? Next step is this list thing, that if there are other variables with the other vertices with the same value. Now in heap, I told you this thing actually doesn't matter, because anyways in the next time when you are pulling the next min, if there are multiple small values, right, then obviously that would be one child with that. So next min would actually call that only. Delete min would actually call the, every time delete min will call the minimum element, right, would pick the minimum element out. So this line is actually not required with heap. You can ignore that. Okay, so if I go over there, because every time you are calling delete min function is taking care of that. If the value is lesser, you are arranging it in the form of a heap, and since the whole structure satisfies the heap property, so anyways it would actually every time you would give you the delete, I mean the minimum element. Okay, so that's the second part. So what is the important part after that? Visited next equal to true. That is, whatever vertex that you got, you are setting that to be true, the visited of that to be true. So here I got the next d as the vertex. I am setting the visited of next d to be true. Same thing. Okay, let's go back over here. Okay, after that, this is the core part. I'm running a loop. for all the neighbors of next v, correct? And I'm checking if the current distance of the neighbor is smaller, or the distance of my next v plus the edge connecting next v with the neighbor is smaller. If that is the case, I'm just modifying this distance. Now in heap, you cannot, remember we told that you cannot modify directly by calling the name because you do not have the index. So you have to use h2v and v2h accordingly, whatever. So you have to use that. So let's check what's happening over here. Same list for v2d in w list. If not visited, same checking. We are what are we doing? Same minimum of yeah, whatever we are doing, we are checking whether it is minimum or the whether h2v of that, I mean this is the same thing, right? h2v is using because you are getting the index of that. So whether the current distance of the neighbor is minimum or the distance of the parent node plus the edge connecting the neighbor with the parent node, that is minimum. Whichever is minimum, you are setting that in this value, and then you are changing the value in the heap by calling the min heap update. So this min heap update was not there. So initially here what we were doing, we were only changing the distance directly. Remember? But now we are using the heap to call the extract mean. Now extract mean, this mean, extract mean, right? This is essentially the analogy of your extract mean or delete mean. Okay. So delete mean is working on distance. So when I'm modifying the distance, I must modify the distance in the heap. And in order to reflect the changes in the heap, I can use the function that I have defined, the min heap update, correct? So this is the updating part. See, I'm calling the min heap update to, if the value is smaller, if I get the minimum value, then I call the min heap update to reflect the same change. Okay, so every time my extract this delete min would have the updated value of the distance, right? Because the min heap update over here has updated it accordingly to the minimum value, depending upon this condition, okay? And this would be my order of log n time. This would be again order of log n time. Okay, and this is basically you are traversing through all the edges, right? If you see this thing now, you are for each of the vertex you are traversing, and then you are checking each edge for all the vertices. So that means you are operating order of edges time. You are checking you are doing this operation the number of edges time. So that means it goes to e log the heap size, log of the heap size, right? Heap size is log n, means log of number of vertices in the heap. So since there are all the vertices we are pushing in the heap, so there are n vertices or v vertices, whatever. So it's e log v. Okay. So that's the Dijkstra part. We can go for the line by line iteration, but also I want to just do the Prim's algorithm first. So how do you want? Do you want line by line, or should I go for the Prim's algorithm? The Prim's algorithm is, I would just copy the Dijkstra code and just change two small things. That's it. Because we told na Dijkstra only change in Prim's algorithm is, I am assuming you have gone through the theory part of it. Okay, if not, please go to that and then come over here in YouTube. The only change in Prim's algorithm is, see, the question that in the starting of the session, Mr. Bimlesh also asked that why setting the infinity we cannot do it 81, right? He also answered that because it's not the path length. Here in Dijkstra we are considering the path. In Prim's we are considering the minimum spanning tree. Now in minimum spanning tree we are only considering the edge weight. We are not adding all the edge weight to create path. So only thing that would change in Prim's is this part. We do not want the summation of edge weights. We only want the edge weight itself. So only change that would be there in Prim's is, see, just a second. So this is the Prim's algorithm. Okay. Okay. Yeah, this is Prim's with heap. Copied code from Dijkstra. This I have even not changed the names. See, if you see the name, this is Dijkstra algorithm only. Everything is same. Only thing that I have changed is I have introduced a new dictionary over here. I have just copied this code with Dijkstra, na? This code, whatever we discussed just now, this code, Dijkstra algorithm with heap. I've just press Control A, Control C, copy that. Okay, and Yeah, paste it over here. So you see that Dijkstra is written. Everything is same. Only changes, we have created a new dictionary now, because in prims we have to in prims and Kruskal we are finding the minimum spanning tree. So basically we have to have the we have to show what is the tree, which edges are there in this minimum spanning tree, correct? Or at least which vertex is connected to which vertex. We are not asking you the distance, we are asking for the vertices, which vertex is connected to which vertex, or which edges are there in the minimum spanning tree. In either way you can answer. So I have used the which vertex is connected to which vertex in this example. That is basically the neighbor. So this neighbor dictionary NBR would actually have for each vertex 0, 1, 2, 3, 4, 5, whatever vertex is there. For each of those vertex, I would have a value, and that value is the parent neighbor. The parent node or the neighbor of that particular vertex. So if I have, say, NBR key is 0 and value is 2, that means my 0 node or 0 vertex is connected with the 2 vertex. Okay. So I've just introduced this particular dictionary to store the vertex incidence relationship. Every other thing is same. Only thing that we have changed over here is, see, I told you, here we are not interested in the path. Initially it was what? DS plus D. See this DS, which delete mean was returning. That is the current distance of the parent node or the next D, so to say. The current distance of the next D is DS. So I do not have to add that in case of frames. I just want the current edge weight. So simply DS plus D, like in Dijkstra, is not required. Simply delete that. If you go to Dijkstra, you would see it was DS plus D. Okay, just delete that, because I don't want the summation. I just want the edge weight. I don't want the path length. Yeah, so delete that. And this line is extra that we have added. Since we have added the NBR, the neighbor. So whenever I'm setting the whenever I'm checking for this minimum value, I'm setting the neighbor accordingly. So the neighbor of my V vertex is the next D. So because I'm visiting next D, right? What did you write over here? For VD in W list of next D, that means all the V over here, all the V vertices inside this, in these lines, is basically the neighbor of next D vertex. So that's why I'm setting the neighbor of V as next D. So this would only give me the tree, right? The incidence of all the vertices of the minimum spanning tree. Okay, so that's the idea. What you do in Dijkstra, you just sum up the minimum, you sum up all the edges so that you get the minimum path. In spanning tree, you did not go for the summation. You actually check whether each of the edges that you choose, whether that is minimum or not. Okay. So both of the cases we are using heap, and again we are simply using the delete mean, because delete mean will every time will give me the minimum value edge. And in Dijkstra we are just taking that minimum value edge and summing and then comparing. In prims we do not have to sum, we can directly compare. That's it. Okay, that's the only change I have done. Delete the DS plus D to plus D. Introduce a new dictionary NBR which shows the minimum spanning tree. And whenever you are changing, just manipulate this NBR accordingly. Set the parent of that each of the neighbor nodes. Okay, so 2 lines of code change, not even 2 lines, just one particular term and 1 line. And if I print it, right, you would get the answer as this is your incidence. That means what this means is the 0 vertex, it is the starting vertex. -1 means, because we have done the initialization over here, right? -1. Initialization is -1, right, over here. So that means 0 is the start vertex, and then 1, 0 means the vertex 1 is connected with 0. The edge between 1 and 0 is the is there in minimum spanning tree. The edge between 2 and 1 is there in minimum spanning tree. Edge between 3 and 1 is there in minimum spanning tree, and edge between 4 and 2 is there in minimum spanning tree. This is NBR. See. And this was the Dijkstra code. If you remember, I have commented this part on, just same as this is the same Dijkstra code. Okay, so yeah, so that's the Prim's algorithm and Dijkstra algorithm, both of them. Now I have 2-3 questions. We can discuss that, or we can also go for line by line iteration of that. But What do you think? What should we do? 2 questions are mainly on Bellman Ford. So if you want, we can do that. Actually, that's important. I want to do that. So it's okay. Is it okay?
Yes, sir.
Okay. Acha, one important point. So I would send all these codes one by one, but also this is there in the index file is there, no? The file where all the codes are there, and in this file, this one, pdsa.iitm. Okay, I have just compiled all the things together like that, and yeah, but the codes are similar. So the prims code that I just showed you, that is not here. That is not present here. So the prims code that we just showed you, that I just showed you, that is, I mean, you can directly copy the Dijkstra code and then understand, right? It's, I showed you what you have to change. Only the ds plus d you have to change because you are considering the edges and not the path, and you have to have a dictionary where you can get the spanning tree. That's it. So that code is not here. You would not find that. So you can copy the Dijkstra and make the necessary changes. Okay. So let's go back to here. This is again very important topic. It's a theoretical topic, but please pay your attention over here. So I would also like if someone responds 2-3 questions, that would be nice. So first is, can Dijkstra work? And can Dijkstra work on negative edges but not cycle?
No, it can't work on negative edges.
Okay. So if it is so, what happens over here?
Because in Dijkstra, if you update once, we don't go back to the vertex. So if it is a negative edges, it's difficult, right? After the iterations also needs to be updated. So we can't do that in Dijkstra.
Correct. But will Dijkstra give me correct result in this case? That's what I'm asking. So let's say, yeah, should be fine. Okay, so this is your start vertex. You apply Dijkstra over here. Obviously, there is only one edge, so you would get 2 for this node, 5 for this node, 6 for this node, right? And then -3. This has already been visited, so I would not change, correct? Because this has already been visited. So I get the result 2, 5, 6. Right? This is Dijkstra is giving me this result. Okay, and if I apply my normal, I mean, if I see what is the minimum distance actually possible, I get 2. That's correct. This all are correct. But if I go over here, oh, sorry, yeah, if I go over here, I can see that it's -3 is there. So if I travel the whole path, so 3, 4, 5, 6 -3, it would give me 3, which is actually greater. Right? So 3 should not be considered, 2 should only be considered. So Dijkstra is giving me correct result. I have a negative edge. Isn't it? Am I making some mistake? Dijkstra is working here, right?
Yeah.
Now see what happens here. Same kind of similar example only. It is not even negative cycle. See, only negative edge. If you sum it up, 3 plus 4 minus 3. So that is 1. It's a positive cycle. So you cannot say it, since it's not a negative cycle, it's only a negative edge, and Dijkstra is actually giving me correct result. But let's say this example. Okay, this is 12, this is -6. Let's say this is 10, and let's say this is 5. This is my start. Okay, since this is my start, okay, these directions are not put. This is like this, and this direction is downwards. Yeah. Okay, so this is 12, correct? This is 10. This is my start. So I'm starting from here, 12 and 10 done. Next, extract mean or delete mean would work. Okay, now I would always tell in terms of heap, so it would be delete mean. So if I do delete mean, what is the minimum value now? 12 is there and 10 is there. So 10 is minimum. I would get 10. So 10 is the next vertex that I would consider. And only outgoing edge is 5. So this is 5. Okay. So next value is 12. Sorry, next value is then 5. Right? 5 and 12 are there left over. Next value is 5, but 5 there are no edges. So just keep it as it is. Next value left over is 12. So I consider that. And I relax the edge which is present over here. So I get 12 minus 6, which is 6 to reach this node. But I have 10. But since this node is already visited by Dijkstra, right? So I cannot actually. So although the length is minimum length to reach this node is 6 by using this particular negative edge. But since Dijkstra has visited this node earlier, while we relaxed this part, right? While we use this part. So that's why I cannot again come back to this node. This is already visited is true. So that's why I cannot modify this 10. It would remain 10. Dijkstra would answer it as 10, but the minimum distance is 6. Okay, even here you see the negative cycle is not there. Not negative cycle. So in both of the cases, we have only negative edge. There is no question of negative cycle, but in one case Dijkstra is working, in one case Dijkstra is not. So I just showed these two examples. The reason is Dijkstra may or may not work on negative edges. This question comes a lot. If someone asks you, can Dijkstra, they give you a particular negative edge and try to and give you in option 4 distances that Dijkstra would give as result. And you simply see, and one of the option would be none of the answer is correct. None of the above, correct? And you would see there is a negative edge and the question is asking for Dijkstra, you do not solve it and directly tick on none of the above. Because negative edge is that Dijkstra would not work. That cannot be done. Dijkstra can give negative edge, correct result in case of negative edges. And in some other example, it may not give. Why? The reason is, now the reason you actually stated earlier, that is the reason actually. See, here we did not encounter, in this example, we did not encounter any such vertex which has to be visited again. Why? Because this is the direction, same direction. We are moving like this. Okay, but if you see over here, we are not getting that direction. Here it is going like that, here it is going this way. But again, I'm not going like this. I'm coming like this. Okay, and that's why what's happening is I am reaching this node first and making the visited of this node true. Okay, why this? Okay, visited of this node true. So later when I get this node, I cannot come back here because visited is true. Here we are not getting into any such problem. So correct, Dijkstra does not give correct result, but it's not that it would never give correct result. It's some example where even negative cycle is not there and only negative edge is there, it may give correct result. So you have to solve.
Is it some sort of topological ordering over here?
No, because in path we do not consider any constraint that the graph must be acyclic. Topological ordering does not come into question unless and until you have acyclic graph, right? When I'm telling you to find a path, it can be cycle. Obviously, it will have cycles. Okay.
I mean, there should be one. There is only one unique path for certain number of vertices. There, the extra might work, right? So if there's multiple.
There can be multiple paths of the same minimum length. That's the answer. There can be multiple paths of the same minimum length. So let's say this is one node, this is 10, this is 3, this is your target. Okay, now got it?
Yes, sir. Yes.
Obviously, there is a cycle. Suppose there is a, not in terms of direction, it's not, because this is going like this and this is going like this. But I mean, physically, it's a cycle. So you cannot do like that. Okay. In terms of DAG, it is a DAG. There is no cycle like that. Is there any cycle? No, there is no cycle. In terms of DAG, it is a DAG, but I was mainly answering your question that, yeah, there is no restriction in Dijkstra that you would have only one path. The answer is Dijkstra would always give you the minimum length path, but there can be multiple such paths of the minimum length. Okay. So this thing was important. Please see that some of us have the idea that, okay, Dijkstra can work in case of negative edges, but it would never work in case of negative cycles. So that is correct. If there is a negative cycle, then not only Dijkstra, it's trivial, right? You can go up to minus infinity. So no algorithm would give there is no question of finding the minimum path. But if there are negative edges, then Dijkstra may or may not. It is not always Dijkstra cannot. It may give correct answer, it may give wrong answer, depending upon the structure of the graph on which you are running Dijkstra. If that structure has this kind of property, where you visit an edge, visit a vertex earlier, and then a later vertex like this one has an edge to that vertex which is actually negative, right? You visit a vertex earlier, and later in your Dijkstra algorithm, there is some vertex over here which has a negative edge over here to this vertex, right? And provided that let's say this is the distance, right? This is u vertex, this is your v vertex. Provided your distance of u plus the negative value that you have got, if that is lesser than the current distance of v, then if this condition is followed, then in such graphs Dijkstras would not work. But if you just make it the opposite way, right, then Dijkstra would work. Okay, so this was happening over here. So this is the condition of checking for whether Dijkstra works in negative edges or not. Now the question is, shortly I would discuss Bellman code also now. Okay, it's late, but I would discuss it, and later you can see on YouTube. Okay. Okay, so what is the idea now? So if I have n nodes to be connected, then how many, I'm considering minimum path, right? Every time Dijkstra, all these things we are trying to find the shortest path, right? And if I assume that all the paths are positive in length, right? So I can always tell that if all the paths are positive in length and I want to connect n vertices, so I would always do that within n-1 edges, because that would be a tree. Okay, I can always do that within n-1 edges. So what is my proposition? My proposition is, considering all edges are positive and I have to connect n edges in a graph, I can do that by maximum. I can do that. I can connect all those n edges by using n-1 edges. Okay, minimum n-1 edges required, and that's a tree.
If it's a connected graph.
If it's a connected graph, I have to connect, right? In order to find the path, I have to connect. Okay, so if that is the case, if I now say that, okay, that was for positive edges. Now, if I say that you have the leisure of using negative edges as well, then can I say that n-1 edges would actually give me, I can connect n vertices by using n-1 edges, and that path would be, that path can be minimum. What I want to say is, path length using n-1 edges, right, is lesser than path length using n edges. Provided condition is negative edges allowed. Okay, is this correct or not? Okay, see, the idea is if I have negative edge, let's say the path length by using n minus 1 edges were, I mean the lesser number of edges were 28, the total path length of n minus 1 edges. Okay, but if I have negative edges, the nth edge that I am considering, I consider n minus 1 edges, these same n minus 1 edges, whatever the n minus 1 edges were here, I am considering the same n minus 1 edges. Okay, but the one edge that I got, the extra one, right, the nth one, that is a negative edge, and let's say that negative edge is around, I mean it's a huge value negative edge. Okay, so what, so let's say that negative edge value is 20, minus 20. Okay, so what would happen, I can use that edge to connect the graph and I would end up with an answer of 80, I mean 8, only 8, right? Same n minus 1 edges, because same n minus 1 edges would give me 28, and this is the last edge is minus 20, so it would give me 8. Correct. So the idea is if only positive paths, positive edges are allowed, then I can connect, I can connect, then let me state it in the other way. If only positive edges are allowed, then the minimum path connecting all the vertices of the graph must have n minus 1 edges. I am stating it again. In order, if only positive edges are allowed, then the minimum path connecting all the vertices of the graph must be n minus 1 edges, must be made up of n minus 1 edges. But if you have negative edges, then the path connecting all the edges and the minimum path as well, right, that can be having more than n minus 1 edges. I mean it can be in n edges, n plus 1 edges, whatever, depending upon what is the construction of the graph. So if this is one differentiating property between negative edges, yeah,
that is due to the formation of a cycle. So
yeah, that is true for the formation of a cycle. See, if I just do this is minus 20. Okay, the last edge that I was talking about. So this was my earlier path. Let's say the summation of these 4 edges was 28. Okay, okay, and let's say not this one, I can do it like this. Let's say this one, this is also fine. So what I would do is, as soon as okay, so in Kruskal, I mean in Bellman-Ford algorithm also, we would just iterate once more. Remember what we did in Dijkstra? We used each vertex and check whether the next, I mean in the next iteration, whether the neighbor is having lesser distance or not. If it has greater distance, I change the greater distance with my distance plus the edge connecting that neighbor, right? So if this is the case in this, I mean in this graph, in this discussion, I initially saw that the summation of all this, right, all this actually made the tree possible. I do not have to have this edge in order to have a connected tree. Only by using these 4 edges I can connect the whole set, and that was giving me result 28, right? But if I add this edge, right, if I add this edge, then I am getting a total result of on even considering any one of the edge already remain connected, I would get a result of 8. Fine. And now since it is not a tree, I can replace any one of them. Remember we used to change the previous distance. So I say, since in the next iteration I saw that I am getting a better result by considering this edge, I would remove any one of the edge which were connecting these graphs, right? Any one of the edge. So remove this one or remove this one. Considering if you want to have the minimum spanning tree, you would obviously remove the one which is highest. Okay, so again it is still a tree. considering which is, see, if I consider this one, this edge is already there, right? If this is the scenario, correct, this is minus 20, and I see that this edge is very nice, it's giving me minus value, but my cycle has formed now. So, and I want the minimum spanning tree. So okay, this is getting a very nice value, I will consider this edge and I would remove any one of the edge which is the highest among others. So considering this edge is highest, right, this edge is highest, you simply remove this edge. Okay, initially you considered this edge, right, and you did not consider this one. But when in the next one of the iteration you saw that, okay, I got this one which is minus 20, right? So I will, any one of the edge I would not take. Any one means not any one, actually the one which is highest. That would give me better result. Okay, for minimum spanning tree. So the main idea that I was saying is, I should say it in other way. You can state it in the other way as well. In n minus, if you consider it in terms of the iteration of the algorithm, so you can just translate this whole statement like this. So within n minus 1 iterations of the algorithm, not in terms of edges. Now I am stating a more proper sentence, which is, this is a proposition. This is what I was just saying to come to this logic. Now this is the proper theory that I am talking about, and on this theory Bellman-Ford is based. Okay, within n minus 1 iterations of the algorithm here means the Bellman-Ford algorithm, we can get minimum spanning tree, or sorry, not minimum spanning tree, minimum path length. Okay, and the other part is, we can get even lesser path length if there is no constraint of having a tree like structure, then you can as well keep the path, as you were saying that it would form a cycle. That is also fine, right? I'm not restricting. That's why I said in Dijkstra or in Bellman-Ford, in path finding, we are not restricting you to have any cycle. You can have cycles, no problem. Okay, so you can have that minus 20 along with this edge. Anyways, it is giving you 8, which is much lesser, the path length, right? So that is fine. So okay, so let's come back to here, the theory part. We can get even lesser value of path length in nth iteration. Okay, so these two are the logic that I'm saying. Within n minus 1 iteration of the algo, we can get a we will. Okay, so let's make it concrete. We will get minimum path length. Okay, that is the path which is of minimum length to connect all the vertices. That is your shortest path which you are finding in this week. So that the proposition is, within n minus 1 iteration of the algorithm, we will get the minimum path. So this is only true. This will only be true when positive edge. Only positive edges are allowed. Okay, but if negative edges are allowed, then in such a graph we can get reduction in the path length even at the nth iteration. Okay, now let us have a little bit refresher of your previous concepts of transitive closure. Okay, what you did remember in transitive closure, there is a matrix which is the adjacency matrix of a graph which shows you 1 and 0. Now 1 means basically whether you can reach from one particular vertex to other. You simply did a square a cube, multiplied that vertex, and what does that tell you? Whether there is a path connecting. If I say in a cube you have 1 between two vertex, which was not there in a square or which was not there in a, and in a cube you have 1. I know that transitive closure was there in your maths or stats. I don't remember, but in maths I think it is there, right?
Yes.
Yeah. So transitive closure in A1 and A2, if one is not there, but A3 one is there between two vertices. What does that mean? That means that there is a path from between those two vertices whose length is 3. Remember that thing, that there can be a path, not a single edge. A1 there is 0, that means there is not an edge.
Yeah, we cannot directly reach, but we can reach via third.
Exactly, we can reach via, but what does, let us be a bit more what should I say, a bit more detailed in that. So what is A1? I was not getting u comma v was 0. A2 u comma v was again 0. Now A3 u comma v gave me 1, right? So this means what? This means that obviously you can reach u to v, you cannot reach directly. So A1 means there is no path connecting u and v directly by using one edge. By using one edge means what? U and v must have a direct edge. So that is 0. So that means there are no direct edges. A2 is again 0. What does that mean? That means I even do not have any path such that there is some middle x vertex, and from u to x and x to v is there. That is also not the case. If that would have been the case, I would get 1 over here. Okay. But if I get A3 to be 1, that means, and this is the scenario, correct. So you have a path whose length is 3 edges, and that's why you got A3 as 1 between u and v. But the matrix of A2 and A1 were giving you 0 because there are no paths of length 2 or 1. So we will just apply the same logic in Bellman-Ford as well. When you actually iterate through the adjacency matrix, right? In Dijkstra algorithm, you are iterating through the adjacency matrix, right? So we will again do the similar thing in Dijkstra, and we would check the neighboring edges, right? And we would check that minimum condition, right? Let me go to the Dijkstra code and show you what we are trying to say. Where is that Dijkstra? Yeah. So let's go to the normal Dijkstra only. It's independent of heap or anything. So this part. Only this part is required. So in Dijkstra, what were we doing? Taking a node, checking whether the neighboring nodes are current value of the distance of the neighboring node is lesser or not. Correct. We were doing that and we were proceeding. So if I do that once for all the vertices, that means is there a direct edge between the vertices or not? If I repeat this loop twice for all the vertices, Dijkstra we were not repeating for all the vertices, we are repeating for neighbors. But simply if I, let's say I write another loop over here, okay, I just suppose remove this next v, okay, for okay, so I just write for v comma d whatever, okay, in, let's say I have a list of tuples where v comma d are there. Okay, so let me just use like this, where u comma v comma d in. Okay, again I have no variable like this. Okay, anyway, so what I mean is basically, let's say I have a list of all the edges in the array, okay, and I want to traverse the whole array. I want to traverse the all the edges, I mean. So in by Bellman-Ford, what you essentially do is, let me go over here and where is the Bellman-Ford? Let me show on Bellman-Ford itself. Yeah. See the same Dijkstra condition. Okay, that's the same loop, the 3 lines that I had over there. Okay, so but see here we are not checking for neighbor. Do you see any neighbor condition over here? I mean, between the first list, first loop. After that we have to check for each one by one. That is fine. But here what we are doing, we just write for u in wlist.keys. That is for all the vertices. We would do what? We would check for edges coming from that vertex, and we would check the distance condition of Dijkstra. Okay, so if I just do it over here, what are we doing? What are we doing? So let's say if a graph is there like this, okay. So 2, 6, 8, 7, -4. So this is the graph. This is my start vertex. How Bellman-Ford works is, so I would not see, I would just start from here, and then what I would do, I would just go through all the edges. No need for checking neighbor and all. Just go through all the edges and simply check what was the value and update it. So I start from here. What is the current value over here? It is initially 0. We consider that, right? So this would be 2. Fine. This would be what? -4. Okay. This would be what? If I travel like that, simply apply the normal, normal steps. So if I go to the algo over here, you would see what? I'm traveling through, just ignore this loop, the outer loop, this loop you ignore now. Just consider these 3 lines, for u in wlist.keys, that part. Consider that part. So what are we doing? We are checking this minimum distance. Again, we are going for the next. See, here we are not using any heap. Are we using any heap over here? Are we checking for minimum? See, what I want to say is, in these 3 lines, we are checking for a particular vertex, the minimum distances. That is okay. But what was the next step in Dijkstra? We again took the next minimum, right? But here we are not using any heap or any next minimum or anything. We are again going to the next I, right? Sorry, next U, next vertex, and then checking for all the vertices, edges from that vertex. It's not mandatory you take the minimum. What's mandatory is you go through all the edges n-1 times. So that's what I'm doing here. So 2 is here, -4 is over here. Okay, so these 2's are done. Next, I would again go to the next vertex. So let's say this is my 0th vertex, this is my 1 vertex, this is my 2 vertex, this is my 3 vertex. Okay, so I got 2 over here, then this is the second vertex, so I take that. Okay, so see, here the value is 2, here the value was -4. According to Dijkstra, I should have picked this one, but I'm not worried about that. What I'm worried about is, according to transitive closure rule, every time I do this process, right, this going through all the edges once, all the edges, I have to go through all the edges once and check for this minimum maximum condition. If I do that, that essentially means whether there is a single path, whether there is a path comprising of a single edge between any 2 vertices. I will show you, just bear with me, just I will show you what I mean. So okay, so I started from here, 2 was over here, -4 was over here. So I kept -4 for this node and 2 for this node. Fine. Next, what is there? I am picking this second node. So 2 plus 6 is over here. Okay, I'm not doing summation. I'm just going through all the vertices, all the edges. So I put 6 over here. Okay, just directly put everything, no issues. -4, 6, 2, and 0. So I got 4 vertices. The value is 0 over here. Here it is 2. Here it is 6. This is not summation. This is not like Dijkstra. We are not taking negative and then adding. Okay, so this is the idea. So now see, now if I check, okay, -4 was there. So if I see that whether there is a path between 0 and 3, right, 0 and 3, I would get that there is no value, right? For the corresponding tuple of 0 and 3 in my list, I would have 0. So that means there is no single path. But if I check whether there is a path between 2 and 3, obviously I would have the value 6, right? This 6. What does that mean? Now that means there is a direct edge connecting 2 and 3 by whose edge weight is 6. Okay, so if I continue this process again one more time, then I would get all minimum path between those 2 edges whose length would be twice. If I again relax all the edges like 3 times, then I would get a minimum path between all the edges by using 3 vertices. Likewise, if I do this process n-1 times, then I would get any minimum path between all the vertices by using n-1 edges, because I have done it n-1 times. And we just discussed that if it is positive, if the edge weights, if it's not here, -4 is here, but if all the edge weights are positive, then we just discussed that if all the edge weights are positive, that within n-1 iteration we can get the minimum path, because n-1 would be the length of the path, that's it. But if the edge weights are negative, then even after that one iteration if we do, we can get a minimum value, because that negative value would come into play. We just discussed -28 and -20. So Bellman-Ford does exactly this thing. It actually first runs n-1 times, and then it would again run the nth time through all the vertices. And that's why this is wlist.keys is there, the outer loop. So this is running n times, correct? This is running n times. Okay, n means the number of vertices. Wlist.keys means all the vertices. So this is running for n times and checking the minimum value, right? So from this, whatever path we are getting, this distance dictionary, correct? So that would have the path length where that would have the path length where each path can be, maybe or may not be, depending upon this minimum condition, maybe or may not be of length n, not n-1. Okay. Now, if there is a minimum edge, then in the nth iteration I can get a lesser value. Okay. And if there is no minimum edge like that, then I can, in the n-1th iteration and nth iteration, how many times I go, I will get the same value. Okay. Now, particularly I have checked in this example, Bellman-Ford, there is, I mean, you would get the result if you run it n-1 times also, you would get the same result as the nth time. Now, the reason for that is there is no path which is smaller while you are considering negative edges and you run it for n times also, right? There is no path in the graph such that even if you consider the negative edge, it would not be considered. The reason is that that visited thing would come, that those edge has already been visited, those vertices would already been visited. Okay, so if you see the output over here, right, this is the output. If I just do it for n-1 times, okay, so if you see that, just a second, it's for wlist.keys, right? If we do that for let's change this to range, doesn't matter anyway. Okay. Okay, so what is the error? Oh, in range we cannot do this thing, right? So I have to put this value somewhere else. Let's say where.
Colon is missing.
Okay. Okay, so we have to, for what I'm doing, I have to get the length. Yeah. You see, if this is the condition, if I just also run it for different times, for I in range where, right? So let's do it for, let's reduce this. Yeah. Yeah. So if, see, okay, even if I do it for -1 times, sorry, -2 times, then also I think it would remain same. Yeah, it remains same. Now, what does this mean? This means there is no further minimization of path, even if you are considering, I mean, so this means basically the number of vertices -2, n-2, n-1 and n, all this length of path, I mean any path of n-2 length, any path of n-1 length, or any path of even n length is not reducing the total cost of reaching, I mean, it's not reducing the overall path length. That means the minimum path that your algorithm is generating, that Dijkstra algorithm or any other minimum shortest path algorithm would give you, would actually constitute of even much lesser number of edges in this example, right? So, or let me state it in the other way, any minimum path from any vertex in the graph, right? The minimum path between any two vertex in the graph must constitute lesser number of edges than n minus 2. Now, if I check it for n minus 3, again the data is same. So any path which is of minimum length between any set of vertices in the graph must constitute total number of edges in that path would be lesser than n minus 3. Okay, accordingly, if I go like this, then I would get a point. See, now it is also same. Now it is 5. I think it changed. Just a second, let me confirm it. Yeah, now it is changing. See, 4 is 9 now over here, right? If I do it 5, see, 4 is 14 now, right? So what does this mean? So in order to reach from the starting node to 4 by considering any path of length n minus 5, I can only get 14 length, right? 14 length is the minimum value by considering a path in which n minus 5 edges would be there. But if I add one more edge, that is if I go for n minus 4 edge, then I get a much lesser value, which is 9. Okay, so in order to connect the fourth vertex from the start vertex is S, right? In order to connect the fourth vertex from the start vertex, I can say the minimum possible length of the path would be 9, and that path would require me at least of n minus 4 edges. Okay, I cannot reduce it further. If I increase it, if I do increase means increase the, if I do n minus 3, that is equal to increasing the number of edges, correct? N minus 3. So that means I am checking with n minus 3 with one more edge. Will I get a lesser path? That is one more intermediate vertex condition I'm increasing, that you are free to take one more intermediate vertex, but give me lesser path. Would I get that? Check. No, we are getting the exact same set of values. You can pause and check, right? But yeah, so I'm getting the same value. What does this mean? That there is n minus 4, n minus 3, n minus 2, n minus 1, n minus n plus 1, everyone would give me same edge length. Okay, even with negative value, we can get that. So that means between any 2 point in the graph, the path that I would get, the minimum path, that constitutes of at least n minus 4 edges. Okay, and n minus 5 is giving me wrong results. N minus 4 edges is the minimum path. So you can actually test that. Yeah. So this was Dijkstra. It's already 9 o'clock. So sorry, this was not Dijkstra. This was Bellman-Ford. We discussed a lot of things, and there are many doubtful things. There are many doubts that would come. I mean, please go through this session once, later also if possible, and all the doubts please write on discourse. We would try to answer it. These 2 weeks are quite heavy, and everyone faces difficulty in these 2 weeks. So yeah, please write your doubts on this.
So like n minus 5 and n minus 4 were like optimized lengths.
Yeah, you can say that I do not have to run the Bellman-Ford algorithm for n minus 3, 2, 1, 0. Right, I can stop at n minus 5, but n minus 4, sorry. But you don't know that until and unless you test like this, right? So actually, after n minus 4, it is running the same iterations, but it is not finding a better path. Even by incorporating more intermediate nodes, it is not able to find a better path. The minimum length has already been reached. Okay.
So the maximum iteration is n minus 1 iteration, right? We cannot do it.
Here iteration is up to n. I mean, initially the code was like this, right?
So n, oh, it's not n minus 1 iteration.
Yeah. See, why n? That's what I was telling you. Why n? The reason is, if there is a cycle, the nth iteration would give me a lesser value actually.
Yeah.
Right? So we got like this. So this is 2, this is 4, this is minus 1. Okay. Now, if I run it only n minus 1 times, which is 2 times, I may consider this edge and this edge.
Yeah.
But if I run it one more time, I will say, oh, negative edge is there, so take that. So it would be total summation would be actually lesser. I may ignore that and take 2 minus 1 total 1. So, but if there is no negative weighted cycle, even if I run it n plus 1, n plus 3, n plus 5 times, whatever, right? It would
Yeah.
always be same. That's the same thing
Yeah.
I showed you.
Yeah.
So that is Bellman-Ford, and that's why Bellman-Ford actually is able to distinguish between negative weighted graphs and positive weighted graph and give you correct result, provided there is no negative weighted cycle. Negative weighted cycle means it's trivial. I mean, there is no question of finding small distance. So Bellman-Ford is able to do that, and this idea is directly from transitive closure. Okay, transitive closure you do if you get at a kth transitive value, right? A of k, the A matrix, adjacency matrix at k. If you get one between two vertex, you know that there is some path which was not available till k minus 1, considering k minus 1 nodes, but using k nodes, I got the path. Using k nodes, I got a path between these two vertices. So similarly, if you run Bellman-Ford till n minus 1 times, then you are sure that if all the edges are positive, that within n minus 1, I would get the minimum path, because obviously a minimum path is basically a tree, and a tree is n minus 1 edges, right?
Yeah.
But if there is a negative edge, then even in the nth case, and in nth case, if I run the negative edge, so overall summation would be negative. I mean, it would reduce from n minus 1. So Bellman-Ford runs till n times. That's why I wrote here n times. All right, it would run till n times, and it checks. So in fact, you can also modify Bellman-Ford in one way, right? But I would tell you how. You just change it in this way, that you run it for at first n minus 1 times. You run this code, normal Bellman-Ford, run it for n minus 1 times. So here you get the distance. Okay. After that, you just come to the outside of the for loop. Run this and keep this thing in mind. Keep this n minus 1 time. Now just copy this for loop. Okay. And copy paste it over here. Oh, sorry. Over here. Okay. And now you check. Now I'm not writing that code. Now you just check whether the distance you get over here, any of the distance, any one of the node would suffice. If that, let's say this is distance, and let's say this is distance 1. I have one matrix distance 1 in which I am modifying. Okay, not like this. Okay, so you have to actually have a dictionary and copy the values and then compare. What I mean is, what you have to check is, you run this code for n minus 1 times, and then you just do this part, run this part once more outside. The nth iteration you do separately. That's what I'm taking. This is the nth iteration, right? One nth iteration. So the last iteration you do separately, and you check whether there is a difference between the distance dictionary of any of the node. Any of the node, if there is a difference between n minus 1 and nth iteration, you can tell there is a cycle, and negative weighted cycle in the graph. So that question also comes. Given a graph, find whether there is a negative weighted cycle or not. So if up till n minus 1 you got a value, but in the nth iteration, if there would not have been a negative weighted cycle, then again you would get the same value. But if there is a negative weighted cycle, then in the last iteration you would see the distance is changing, because by considering that extra edge, you are getting a lesser value. Fine. So this is again a good question that may come. I mean, not in this exam. I mean, somewhere you may face that. Use Bellman-Ford to predict whether a graph has negative weighted cycle. Mind it, negative weighted cycle, not a negative edge. This will work for negative weighted cycle only when the overall value of the cycle is negative, it's not positive. Okay. So in that situation, you run it till n minus 1, and if you run it once separately one more time, check whether there is change in the distance value of even one vertex. If in the nth iteration there is change in even one vertex, you can directly say there is a cycle, and that cycle's overall summation is negative. Okay, that also, just this thing would give you that beautiful result. Fine. Okay, so you have to compare these two distances. I mean, just copy this distance in one separate temporary dictionary, and then over here you modify the distance and compare whether over here after here.
So basically, the dictionary, both the dictionary will have the same keys, and then values, if at all, any for any of the keys different. That is what you said.
Sir, we'll just compare these two dictionaries, and if they're not the same, we'll return like
Exactly. Just store the temporary distance temp value. Sorry, dictionary. Store it in a temp dictionary, right? TMP. Okay, and then you do a comparison of this dictionary. Store this temp and compare this with dictionary. I mean, temp with dictionary. If there is a change in the nth iteration, you just directly print out there is a negative weighted cycle. Negative weighted cycle. I'm repeating it again and again. Cycle. Negative weighted edge cycle, not edge. Because if it's an only edge, which would not make any difference, right? So you see in this example as well, there is negative edges also. -1, -2, -4. But we just saw even by using this as minus till -4, we were getting the same result. -4, -3, -2. Why it was so? The reason is even these edges are there which are negative, but they are placed in such a manner, they are between these two vertices, that they are not actually affecting the minimum path then. Right? You know how the minimum path is calculated. Take one, then again proceed by one, check the visited property, right? So you do that. So that would not affect. Okay, so negative weighted cycle. Okay, so that's the idea. Just link the idea of Bellman-Ford with transitive closure of your linear algebra that you learned. I don't know, linear algebra maths or where did you learn it? In CT maths? I just CT, right? Yeah, I confirmed that you all have learned it. That's, yeah, before discussing this. So yeah, just compare that with transitive closure. This is the exactly same idea. Every iteration of this outer loop is actually telling you so let's say the kth iteration of this outer loop, which is highlighted now, tells you what is the, so at the kth iteration of this loop, the value stored in distance essentially tells you the minimum path considering k intermediate vertices, or sorry, not k intermediate vertices, the minimum path considering k edges to reach every pair of vertices. So the kth iteration of this outer loop would store the value of the path, minimum value of the path, considering k edges in the distance dictionary. Okay, just like transitive closure. And if I get n vertices are there, and if I get n-1 iteration, then if all positive, I would obviously get the minimum path. But if nth iteration I get again a lesser value, that means there is a negative weighted cycle. And you can say that it's, it's a negative weighted cycle. You can print that. Okay, so that was Bellman-Ford. Prim's, Dijkstra, Bellman-Ford, Heap, all these things we discussed. I think the binary tree was left. Binary trees, I hope you would be able to figure that out. That's quite easy. There is nothing difficult. Just see the theoretical concept, map it to the code. It should be fine. If any doubt is there, please post it on Discord. We would discuss. Fine. Oh, Floyd-Warshall is again there, but okay, so that also Floyd-Warshall is again not that difficult. We are just iterating through same. Here in Bellman-Ford, we are considering k plus 1, k plus 2 edges. In Floyd-Warshall, we are considering vertices, whether using up to k vertices or k minus 1 vertices or k minus 2 vertices. That's the idea. Okay, but again, if you want to have a proper discussion of Floyd-Warshall, we can have it on the next live coding session. After live coding, we can discuss Floyd-Warshall. Okay, I think it's on Saturday, so we can discuss on that.
Live coding is on Sunday, sir.
Sunday, okay, actually, fine. So I think Atul Bhaiya would take that. So if you all want, okay, anyway, we would discuss first Floyd-Warshall on that. No issues. Okay, and okay, there are many things in these 2 weeks considering together. I would request all of you to please post your doubts on Discord, sir. Even regarding the Kruskal algorithm, the union find. Union find is actually easy. There is not much difficult things. What is, we are just simply, we are using the union and find. You see, simply finding and then setting the component. We are just using it as a tool. But still, there are doubts. I think there would be doubts. Please post it on Discord, and we would have a definitive answer on Discord. Fine. And Floyd-Warshall, we would discuss briefly on the live coding session after the coding, or maybe before the coding. Fine. Okay. Any doubts? Any other?
Yeah, just one small doubt. I don't know whether it's a small doubt. In Prim's algorithm, this minimum that spanning tree problem, in the code, where do we check for whether the tree edge we are adding is a cycle or not. In the code, I'm unable to.
Very good. Very nice. See, if I
Because
go to the,
theoretically it was easy. I was studying only theoretically, but in the code, I'm unable to locate that thing.
Got it. See,
Can you say without heap, because heap is very difficult for me. Still
Okay,
yet to go to heap. Yeah.
do I have the normal prims over here? Yeah, this is prims, right? Yeah. Okay. Fine. So yeah, this is normal prims, right? Yeah. Okay. So here, see, when you are picking a node, so this is the first picking a node, right? Minimum node is picked. Then
Yes.
creating the list of all the nodes with a minimum value.
Yeah.
Fine. Then you're setting the visited of this node to be true.
Yeah.
Let's have a dry run along with the code. I don't know how to have. Okay, wait just a second now. Okay, so yeah. Okay, so let's say so this is one vertex. This is the start vertex, which is 0. Okay, this is one vertex. This is one vertex. Okay, let's yeah. Okay, and let's say this is 10, this is 5, and let's say this is 15. And let's say this is 4. Okay, now see, obviously first we would pick the 0 vertex, and what are we doing after that? We are picking the all the values which are 0. No value has 0, so I pick that, and then I go to all the neighbors. So I go to all the neighbors and I set the visited of 0 as true. Okay, then I go to the over here, I go to all the neighbors of 0. Okay, and then what I do, if not visited, none of them are visited, is the first iteration. I set that either the, I check whether it's the minimum distance. Now initially all of this would be infinity, right? All of this would be infinity. Okay, and I set the distance to be either the whichever value is smaller. So whichever means what? Current distance v means the infinity, and your d means the edge weight, right? Edge weight, yeah, the edge value. So I would take here 5. In place of infinity, I would replace it with 5, because 5 is the edge value.
10 there.
Yeah. What I am doing. So here I would replace it with 5, and here I would replace it with 10. Done. Okay. Now, okay, so both the neighbors are done. So after that, what I would do? This is visited. I'm just writing v on top of the ones which are visited. Okay. Next, I would go to the next iteration and again finding the minimum value. Now the minimum value 5 is there, 10 is there, and infinity is there. So I would take 5, right? So I take 5 over here. So 5 is visited now. This line, right? Visited of next v is 5. So sorry, the next v is essentially the vertex which is 5, and I set the visited to be true. Now see, I have considered this edge. So these two are actually connected, but I have yet not considered. So if I draw the tree accordingly, what is the current position of the tree? So this node is there, the 0th node. Then I've considered the next visited, which means this is visited. These two are visited, right? So whichever is visited, that means that is there in your tree. I mean,
Yeah.
right? So yeah, so this is done. So this is the current state of my tree. This is the graph. Okay, so this is 5 is done. Okay, fine. So after that, what is the minimum value after 5? Oh, I have not reduced this value, right? So this would be 4, because this is again the neighbor of 5. Okay, so when I check for 5, I would reduce that, and let's say this is like this. This edge is pointed in this direction. I'm not saying the directions. Okay, yeah, fine. So this is a cycle. I mean, this is forming this cycle, right? Now see what happens. I have this is 4. Next one. So I take the minimum value 4 over here, which is 4 and 10 is there, right? So I take the minimum value 4. Fine. Now see, I have got two options. I mean, obviously I would take 10, right? And I consider the minimum value, which is 10 now, and then I take the vertices from 10 to the vertices where I can see the neighbors. Correct? Got the point? So next is 10, right? So the next only leftover value is 10. Okay, and that is not visited. Is it getting the point? So initially it was 10 over here. So 10 was there, 5 was here. So I took the 5 over here. Now 10 and 4, so next 5 I considered. So I considered 4 along with it. So 4 was here, 4 was added. Now 4 and 10 were there. So I considered the minimum value among them, that is 4. I joined this. So this is my current state. And then I would consider the next value. Now next over here I am reached, and 10 is the minimum value which is there. So I add 10 over here.
Okay.
This is the process. Now see, this was actually creating the problem. Now if I actually try to add this vertex, you see that this condition never arrived. The reason
Oh.
is this is visited.
Okay. Yeah.
So essentially your cycle checking in case of code is done by your visited property.
Okay. Thanks a lot. Yeah, because I was a bit confused with the theory and the code. Where are we checking? Thank
So if you want to say which one is checking for cycle, this condition. I mean, not this condition actually. Yeah, if not visited.
Okay. Yeah, thank you.
Okay. Yeah. Okay, and another thing I would tell you that since you are telling about the cycle thing, now I don't know whether you have gone through Kruskal's algorithm or not.
Yeah, not the code, but yeah, theory.
Just a second, I'm just showing that. The union find thing, I'm just stating, since this would be a bit confusing. So in Kruskal's also we check for cycle, correct? But if you go to the Kruskal's code, yeah, over here, okay, I know you have not gone through the code, and I would discuss it. I don't know when, but you have to discuss it sometime. So maybe in the next week's first session, I would discuss this code.
Yeah.
But you see what's happening over here. Here also we are not. I'm telling you in advance. Once you go through the code, you would understand it. So you would also say that here we are also not checking for cycle in that very explicit manner. Okay, in that place it was using visited, but in this place the cycle checking is not done like that. It is actually happening as a part of this condition component. Now see how it is happening. I'm just give you a brief idea. Component means if let's say if these three I'm in the middle of a tree construction state. So let's say these two are the current component of trees that have been created by considering Kruskal's. Not this one. Okay, just a second. So these two are the components of tree. This is component 1, this is component 2. Kruskal's you know now, because we just simply pick each of the edges one by one. So
Yeah.
it may be the case that I have these two as the minimum and the third minimum is separate. So it may not be joined with it. It may not be the case. I may have a separate component totally growing separately.
Okay.
In Kruskal that happens. So if I have two different components which grows separately, right? And what I have to do is how that cycle checking is work. So let's say if there is a edge like that, which I can add, but let's say that edge creates a cycle. Let's say somehow if I have to add this edge later also, then that is creating a cycle. Okay. So if this is the case, if some edge is creating cycle, how we can actually, how Kruskal actually checks for that is in the code you would see what happens. What is happening is, see, uh, all the vertices of this particular separate tree would be having one component, right? So let's say if this is C1 component, so this will also be C1 component, that they belong to one component.
Okay.
And this would belong to the other component, C2. Okay. Now, how can I check whether a particular edge is creating cycle or not? So let's say for confirm, I would take a edge which creates a cycle. If I join this one, this is a cycle, correct? Proper cycle.
Yeah.
Okay. If I join this one, this is again a cycle, correct?
Yeah.
What is common in these two things? The
It
common is
belongs
that
to the same component. Right?
exactly. The vertices that I joined, they belong to same component.
Oh, that's the
So,
condition satisfied
so
there.
if you go to the Kruskal's code, you would see that condition. Where was it? Wait just a second. Okay. If the components are not same, then only you proceed.
Okay, union happens. Okay. Yeah.
Got it?
Yeah. Thanks.
Yeah. Okay. So yeah, I would again ask you, many of the points we could not discuss, please post on discourse. If you have doubt, post the part of the code where you have doubt, underline that part, and I would try to answer. Right. Thanks. Okay, any doubt you want to
For
ask?
week 6 or at least couple of days extension should be.
I know. We were also discussing that within the team that week 5. See, week 5
Yes,
is
sir.
actually the
We
algorithms.
haven't,
Yeah.
we haven't like I haven't personally started week 6 yet, so that's the reason, sir. So,
Yes, so no time because this algorithm takes a lot of time. Really don't have, and that topic is also very tough. Heap
It is
really
tough. It is very tough. And see,
When
the
you
problem is now, that's why I asked whether we have
sir,
learned
you told, sir, you
basic
told
data.
these were,
Yeah.
sir, you
Just a
told
second.
these. Oh, yes, sir.
Just a second. So that's why I told that the problem is in normal pedagogy of this PD. I mean, not PDS in terms of algorithms. I'm saying the normal convention is generally we actually go for data structures basics first, and then we learn algorithms using that data structure. If you see, even in our course, week 5 you learn the algorithms first, the naive way to implement them. Week 6 is mainly the tools like heap, like binary search tree, right? And then you use those tools like union find, and in the same algorithms that you learned, you apply them. But the problem here is we are studying the tools as well as the algorithm together, and that's why it's quite difficult. Let us see what we can do.
this takes a lot of
In week
algorithm.
6, for week 6, if we can extend till 15th, that will be a great help.
Okay. Let me talk with the operational team also. Okay, fine. We would try.
Sir, in regard to the concepts, week 5 and week 6 are like very heavy with compared to all the 12 weeks, or like how?
See, week. So let me state it this way. Week 5 has a heap, union find. These two are the tools which you apply in the algorithms of. Sorry, week 6. These are the tools which you apply in the algorithms of week 5, right? Similarly, in week 5, you also learned a bit of binary search tree. So, but we have not applied that in any algorithm as of now. So the algorithms where you would apply the binary search tree, those 2 or 3 lectures would be difficult, but after that things would turn easy. Okay, so this part is the actually the bell curve top. I mean, in normal distribution, you have that top part, which is in terms of difficulty. This is the week 5, 6, and maybe 7 also is a bit difficult. After that, it should be fine. Okay. Fine. Okay.
Thank
Thanks a
you.
lot. Thanks a lot.
Thank you, sir.
Thank you.